Hey, so yeah, I said, I work on autonomous drones. And when people typically think of autonomous drones, oh, can you hear me well enough there?
Yeah, hear you good. Go ahead.
Yeah. So then when people think of drones, they typically think of this kind of thing. So this is a quad rotor and it's an autonomous drone race. So it's a race we did in 2019 before COVID. And the drone had to race autonomously through this track. There were like 480 teams joining, and yeah, this was actually our winning run, which at the time won us $1 million. So we were very happy to win that one. We lost some other races before, so this was the one to win. But yeah, this was a drone, and I will give a little bit more details about it. It's a typical drone, I would say, that people think of. But in our lab, we focus on very small drones as well. Very tiny, lightweight, agile drones. I hope you don't see this whole menu on your screen, do you?
No, we see only the slides.
Oh, perfect. Yeah, sorry. Yeah, okay. And if you look at the screen now, and yeah, this is something I would love to show you also in real life, is the Delphi Nimble. So this is a Delphi. It's a flapping wing drone, and it's inspired by flying insects. And yeah, the special thing about the Nimble was that it could steer with the wings, so it was very agile. And we could mimic the escape maneuvers of fruit flies. And it was so similar to that of the fruit fly. Here you see some maneuvers like going front and back really quickly. But it was so similar to the fruit fly that we could actually, this is one of those turns. If you try to swat it from the left, it would escape to the right. And it was so similar to the fruit fly that we could explain some things that biologists didn't know yet about these kind of maneuvers. And yeah, I'm not going to talk too much about physics or aerodynamics today. So I'm going to talk about autonomous flight. And when you think of drones, then the main challenge there is size, weight, and power. So on the left, we have the drone that was made by the drone competition. It weighs 3 kilos. So it uses 600 watts to fly. And it has an NVIDIA Jetson Xavier, which is, yeah, pretty good compute unit. It has 42 gigabytes of memory, and it has lots of GPUs. And so they were very happy with that when they told us about it. But we ourselves, we actually like much more these smaller vehicles. So on the right, you have the Delphi. It weighs 29 grams. So that also means that to fly, it only uses 6 watts. And the processor on board is just a STM. So it's a microcontroller with 192 kilobytes of memory. Now the question becomes, if you want to make these vehicles autonomous, and this vehicle is like 100 times lighter, so it's really a lot lighter than the other one, this is challenging. So most roboticists, when they make drones autonomous, they use simultaneous localization and mapping. So they make highly detailed 3D maps of the environment. You see such a map on the right. You can make it based on vision. And typically, already a medium space like the one you're sitting in now, it's like hundreds to thousands of megabytes of memory to store it. And we're not even talking about building it with processing. And obviously, the Delphi cannot, have this even in memory because it has only 192 kilobytes here. Now, you may think, okay, there's an alternative approach. We can use deep neural networks like deep reinforcement learning, something like that. But yeah, these embedded units like the NVIDIA Jetson or others, yeah, they're actually still too heavy. So 85 grams, it uses 7.5 watts. Yeah, if you look at the Delphi, basically the NVIDIA is already 3 times as heavy as the Delphi itself. And it uses more power to think than the Delphi needs to fly. So that's also not an option. And yeah, this paints a kind of grim picture because, yeah, is it even possible, right, to make these drones autonomous, and how to do it? Now, of course, actually, we know it's possible because, yeah, especially in the summer, we see many insects. So I have these fruit flies in my kitchen. I don't know if you have that, but you have honeybees, of course. And this is a honeybee, and these insects are actually amazing. And so honeybees can land on flowers even if they move in the wind. They can build their base station. They call it the hive. They can navigate, so they can fly away really for tens of kilometers and come back to the hive. They communicate together. So if they find a very nice flower field and they're enthusiastic about it, they do these waggle dances in the nest. And they tell other honeybees which direction they should follow. They also take group decisions. So when there is a new queen, the old queen has to move out, I believe. And then there are scouts, and they look at different places, and then they advertise them in the nest, a bit similar to the waggle dance. And then they choose together to which place they're going to go. So they take these group decisions, and they can recognize complex visual patterns. So you can even, train them to get nectar at a specific phase instead of another one. So yeah, it's really impressive. And they do this with only 1 million neurons and very lightweight sensors. So yeah, to me, it's obvious that we should look at nature if we want to make tiny lightweight drones autonomous. Now, one of the main strategies, I mean, there's multiple strategies they use, but I also don't want to go too much over time. So one of the main strategies is that they actually solve complex problems with the help of simple behaviors, which they link together in a smart way. And so what we see here is, I must say personally, it doesn't look too good to me, but I think to the fruit fly, this is a delicious strawberry. And what we see here is the trajectory of the fruit fly over time. And what happens, I don't know if I have my camera, but if the wind comes from the side, it will go orthogonal. Yeah, you see me? Okay, great. So if the wind comes from here, it will go orthogonal to the wind. So this is called casting. And then when it smells the fruit, it will go upwind. They call that surging. And then when it loses the scent again, it will start casting again. And you see that here. It apparently lost the scent, but then found it again and moved towards a strawberry. And so two very simple behaviors solve a very difficult task. And this is mostly the main way in which they find your fruit in your kitchen. If you look at robotics, then there's many robotics solutions out there. They try to model the world. They try to model the complexity and try to put that in the brain of the robot. And so you typically have like the environment, and then you have the probabilities of the gas source being somewhere, and then you smell a particle, and then you have the wind field, and then you try to model the probabilities that it came from different points. And this is a lot of calculation, and basically it tries to internalize the complexity. But that's not what insects do. They solve difficult tasks by linking together simple behaviors.
By the way, Guido, this behavior that you just showed here is what Bing Brendan is going to talk about in the third week. They did also work on training a recurrent neural network to do this casting and odor plume following. It's really, really nice work. You can hear about the third week here. Also remote talk.
Cool. Yeah.
Okay, go ahead.
Okay, I would love to hear that. Yeah. So machine learning is an option there, and then I would love to hear that. On the left, we have a Delphi. It's going a little bit slower, I guess, over the internet connection, but we speed it up here a bit. So this is a Delphi, and it weighs only 20 grams. And it flies completely by itself. This was in 2013. We had a small stereo vision system on board with onboard processing, actually the same STM. And it was doing all of this. It was not doing a task, so it was just flying around, but that was already challenging enough, I must say. And it was by linking together these behaviors. So I will show the brain in a second. On the right, there's an even more difficult task. And so there's a swarm of, in this case, 4 tiny drones. So these are crazy flies, so that you can actually buy them at BitCraze. It's a Swedish company. And they have tiny lasers, so they can detect objects. They can also go into doors. And they have radios, so they can also sense when another one is getting close, and then they can avoid each other. But they can also notice like, hey, there is already a drone in this room. and it's going to the east, so I go to the south. And so they spread out, they explore the environment. We put little cameras on them, but this was just to save images. So it was not used for navigation. And then they can get back to the beginning point. So they can do this, yeah.
But they don't have a full LiDAR, right? They have like a laser distance sensor. One of them pointing forwards or multiple distance sensors?
Yeah, so they have 4 tiny lasers in the 4 orthogonal directions.
Okay.
Yeah. So, and they have a little flow deck that looks down. And so it's a camera with a little laser down, and that determines the velocity. So then they know how fast they move. And that's more or less it. They still have radio, so they use the signal strength of the other ones. And if somebody gets really close, then one of them gives priority to the other one. And so it's a very hierarchical society, this form. And then, so they use bug algorithms to make it to make this exploration possible, which is something we published in 2019. And at that time, even big drones, like 3 kilo drones, did not do such a complex task yet. And if you look in their brains, let me see. Yeah, so if we look in their brains, it's actually simple finite state machines. And so left, the states the behaviors are in the circles. The funny thing is actually 3 of the behaviors are to fly straight, and 1 of them is to turn right. But the intelligence is in the links. When do you turn, when not? One of the problems was that the Delphi could not hover, and so it always had to keep on the move. So this was actually quite a hard problem. But with these simple behaviors, it was able to never, I mean, theoretically, if the stereo vision was perfect, it would never hit an obstacle. And on the right, we have,
Could you fly that Delphi in this room with all these people? Would that actually have worked at that point?
Yeah, I actually did demos with it. So I was at ICRA this year, and someone knew me from a long time ago, and I was in Paris, and I was just in a room I never saw. I could just fly it. It was really reliable. It couldn't handle dynamic objects, so it was assuming static objects. So but we actually had, it was a little bit more complex than this. Like we had a kind of emergency procedure, that if somebody would jump in front, it would immediately turn. But the problem of that is that if you immediately turn and you have a small field of view, which was our case, you could turn into another obstacle that you didn't see. But but it was working very robustly actually. We did demos, no problem. The room you're in. And so the right one is, the behaviors are a little bit more complex, like follow wall, but I mean, it's very simple. It all runs on a microcontroller. So just, at this level of abstraction, by doing these simple behaviors, you can get very far. But I don't think you can do everything. And that's why actually I started to look at neuromorphic sensing and computing. Because my personal feeling is that, at some point you need to process high dimensional, like visual information, for example. And then the microcontroller becomes a problem. You actually need the parallelism of neural networks, basically. Since we cannot use the conventional computing, it's too heavy, too energy demanding. To me, that's the promise of neuromorphic sensing and computing. And so that's why I started to focus on that. And it basically goes into your question, Toby, like we had the 4 lasers. This meant that if you had a wire or something, the laser could miss it, and then you would fly into it. But with vision, if you have a broad field of view, you actually can see many things. So also flies, they are amazing at obstacle avoidance. And so that's,
And you're not going to land on a flower with that crazy fly. Can't land on the top of a chair or something. Your crazy fly just doesn't have enough dimensions of input. Yeah,
exactly. You can do, your vision is such a rich sense, so and our goal, in the lab is we want actually fully neuromorphic vision-based autonomous flight. And so, of course, also other sensors, by the way. But why fully neuromorphic? Because, yeah, it would be nice if in the end you only need a neuromorphic chip, right? So that you don't need another companion processor for other stuff. And so if this is the most, energy efficient option, and so that's what we've been trying to work towards. And we're not there yet, but we did make some nice progress. So I would like to tell you a little bit about my journey without hopefully boring you too much. And so, and we're going to do that in the context of a case study. So yeah, I say optical flow landing. So I will be mostly talking about landing, but I will also be showing some results about optical flow control, just ego motion. So ego motion control. So I'm first going to show you a very good landing system. I guess you can already see what it is, right? So honeybees are, of course, very apt at it. And biologists looked at these animals and they looked at vertical landings. And then they plotted the approach speed, so the vertical speed, versus the distance to the landing surface. And you see that there's this like perfect line, right? And so basically, as they go down, the honeybees keep the relation between distance and speed constant. Now, and this made the biologists realize that they were using optical flow divergence. Now, to illustrate that in the context of a drone, so we have a drone here with the camera looking down, and then, if you go down, what you see becomes bigger. I hope you see this video of the flower getting bigger. You see these blue arrows, it's the optical flow. It will be going outwards. And the divergence of the optical flow field, if you work out the math, the divergence D corresponds to the vertical velocity divided by the height above the flower. And they keep this constant, the honeybees. Now, what happens if you keep this constant? Then when you're at 10 meters, going down with 2 meters per second, then at 5 meters, you're going down with 1 meter per second. And at 1 meter, you're going down with 20 centimeters per second. So basically, you will make a very soft landing. And biologists, of course, love this, before I go to this slide, because you only need vision, basically. You don't need any height sensor. So when I started this, it was at the European Space Agency, and they didn't want these heavy radars or lidars to land on planets. They just wanted a little bit of vision to basically land. And so that's cool, but and it sounds simple enough, but it's actually not so simple to implement this strategy. So I will show you what happens if you do the naive approach. So what is the naive approach? It's also the approach that people employed, the first ones to try it. And so we have the thrust, the excess thrust, and we set it to a gain, a control gain, just a proportional gain, times the error in the divergence. So suppose you want to land, then you have a desired divergence, so you want to go down, you want to have a certain expansion of the flow field. And if it's not expanding, then this is lower, so you have to thrust less. So you need to go down quicker. If the divergence is too big, then you're going too fast down, so you need to thrust more. And so I'll show you what happens if you implement that. And the first time I actually found this out was during a demo at the European Space Agency. And they were applauding in this part of the landing. So you see the drone going down, hopefully. Oh, the video.
And you maybe, I don't know if you have a lot of videos, very nice videos. Can you change the video sharing mode? With the 3 dots. You have those 3 dots at the top of your Zoom control, and you change for video sharing to speed up the frame rate at the cost of resolution, special resolution. Do you know those 3 dots?
Yeah, I see it. I see record, captions, reactions.
You should have a way to change the sharing mode there to video sharing, video optimized. And especially if you have sound, you can share the video sound.
I think you have to activate the sharing mode and reshare your screen again, and then you will see that.
Yeah, you can share the screen again and turn on this video optimizing mode in the sharing, but usually you can do it during the sharing. This,
I can. On the bottom left corner of the pop-up window.
Okay, so in the bottom left, I just have my mute and stuff. I see
Share
share.
screen. Yeah, you have these two little check boxes.
So I see share screen. I have
you just click share
advanced.
screen and you have a pop-up window. And on that small window, on the bottom left corner, you have those options.
Oh yeah,
Wait.
optimize for video clip.
Yes.
Yeah.
Okay, I can't click that. It doesn't want me to click that. I don't know. I have share sound. Yeah, sorry, it won't optimize for some reason.
Oh, it's okay. You'll just describe what's going on here with your, like, in words.
I'm sorry.
That's okay.
It's impressive anyway.
Yeah. And so what happened when you did this demo?
Yeah, so actually the video stopped just before. Okay,
You got
now
the
the whole
Gates
program
effect.
is.
The Bill Gates effect.
This is nice. Okay, I don't know what happened there.
There's not a soft landing.
No, I've seen that. I've seen that before too with PowerPoint. It just crashed sometimes with video.
Yeah. The PowerPoint doesn't negotiate.
That's what happened. That's what happened during the demo. Okay, let me try this again. I hope it will work this time then. Can you see this?
Yeah, we see it landing. It's coming down. Yeah.
Yeah, so when it gets close to the surface, I hope it won't stop this time. Yeah, so what you see is that it's going up and down, you know,
Oh,
so
yeah,
it starts
bouncing.
to, yeah, it's really bouncing basically, which is obviously, you know, at first they were applauding this idea because it looked good. And then close to the ground, when it started doing that, they started laughing at me basically. And so I guess, you know, the lesson I learned is never to do a demo when you didn't try it out yet. So that's one lesson. But the thing is that.
But
Sorry?
what is this D star that you choose? Why do you choose a desired divergence instead of just, you know, you kind of skipped a step there, right? You skipped one step. You want to achieve some divergence, obviously, right? Because otherwise you're not landing. So that's
Yeah, exactly.
Right? You have a target of some divergence, which is sort of how quickly you're landing. And
Yeah,
then,
so the main challenge with optical flow is that also if you take your motion, yeah, so for example, if you want to go down, you need your divergence to be positive, let's say. So you want, you know, this flow to go outwards. If you want to go away, you want the flow to go inwards, like you want negative divergence, for example. So, and then of course, the faster your divergence, the quicker your approach. So you can basically determine by controlling your divergence how quickly you approach it. But the challenge is, and that's also the reason of the oscillations that you saw. So I hope now I can show that. Yeah. So this divergence, like I said on the slide before, it's the vertical velocity divided by the height. So let me get the laser pointer here. So basically, velocity and distance in optical flow are entangled. And you cannot disentangle them like that. So I cannot say I want to go 1 meter per second. So I can only say I want this optical flow. And the problem is that what happens is that when you get close to the floor, this set becomes very small. So the divergence is going to be huge, even for very low velocities. So you have this very simple control here, and you want some divergence, but the divergence you measure, you know, it becomes huge. And then if you use that immediately in the thrust, then you're going to give very large thrust, very low thrust, and you get this
because of delay, it goes unstable.
Exactly. Yeah. In aerospace, we call this pilot-induced oscillation. And actually humans have it too when they do visual only approaches. So they can have this too. So and there's a whole story about this. Yeah, Toby knows it a little bit. Because basically in this paper here on the bottom, I analyze this and I say like, hey, you can use this instability or the stability properties of the control, you can actually use it to disentangle velocity and height. So you can actually see distance in an active way by playing with your control. But that's a topic for a different time. Else I will go hugely over time. But this just to show to you that optical flow control is very relevant. Insects do a lot with it. And it's not super easy. So it's a nice task, I think. It's relatively complex, but it's also not, the most complex task ever or something. So it's a nice task to study. And if you look at the drone that you just saw landing, it had a very conventional pipeline. So what is that? So we had a camera, a CMOS camera, images. We detect corners in an image. Then we go to the next image and we track the corners to the next image. So if you find the same corner, then you have optical flow. And then we fit the flow field to detect the divergence. And we use this in our controller and we send that to the propellers. So we send the thrust command. So I make the box red here because this is completely conventional and we would like this to become neuromorphic. And I think I need,
have a question
tell
for
me.
you. What is the most expensive component of it? Is it the ransack or is it just the matching of the corners or the corner detection? What was the computational bound there? With this method, which is definitely effective, it works for sure. But what is the most expensive step there?
Yeah, so here, the corner detection was pretty expensive and the flow tracking. Those were the most expensive steps. Of course, there's many different algorithms to do it. And I made actually many highly efficient algorithms that don't process the whole image, but locally look for corners, for example. The flow we were using Lucas Canade, it's kind of fast. It's like an iterative method. So most people would use fast corners here, but those corner detection and tracking are the most expensive. The flow fit here was pretty quick, but yeah, it costs some computation time. But the image processing tasks are typically the bottleneck. And this is also exactly why, my point before, like in the control part, and what you saw with the Delphi Explorer and the swarm, it was all innovation in this part. Like, let's not make a map or do path planning, but let's do some simple combination of behaviors. It's on this end of the pipeline. Yeah, I don't know if you see my mouse, so I'll get a laser pointer. Yeah, sorry. Yeah, so it's all on this part, but this is actually computationally quite low. And here, this is very hard to get rid of. If in the end you want, complex visual information, you need to do something here. And when you do image processing on a microcontroller or CPU, it's gonna be sequential, right? So that's the problem.
So I have a question here.
There's a question here.
So what made you choose divergence? There are many other functional forms you could have chosen. Why did you choose this form?
Why choose divergence and not some other functional form? I think it's from the biology. Right?
So the study I mentioned does vertical landings. And I don't know if you remember the video of the flower. Yeah, it doesn't render so well online, but the flower gets bigger, right? So this getting bigger, the expansion of the image, that's captured by the divergence of the flow field.
I see. Okay.
Yeah, but you can, and that's why I said, we're going to focus on landing first, but at the end, I do other motions. If you move to the right, you also have optic flow. So suppose you look down, but you move to the right, and then you see flow to the left. And that's, we call that ventral flow. So, but it's not divergence. So that's just flow, basically, translational flow. And you can also control that. So that's, in that way, you can actually completely control your 3D motion. Yeah. Okay, so red is traditional. So in our path to making a neuromorphic pipeline, we did many things. We did some things off board, not in the control loop, it's orange. we did something on board and in the loop, but we actually simulated, for example, a spiking net on a conventional hardware. So we colored that in dirty green. And then we have nice green, which is on board, in the loop, and neuromorphic hardware. And so we first studied event-based cameras. So we had an event-based camera, so that's green. But then we had a CPU that took these events and used a local plane fitting algorithm to get flow. And then we actually were doing the same plane fitting. This is 2018, published in 2018. It was actually the first work to use a DVS in the control loop of a flying drone. We were a bit surprised by that. So you see the drone landing pretty fast. So we will also show it in slow motion. So here it is. On the right, you see the events and you see the flow vectors in yellow. And yeah, it's basically doing an extremely quick divergence landing. And so here we were doing divergence is 1, which means that at 5 meters, you're going 5 meters per second, at 3 meters per second, etc. It was the fastest landing we ever did with optical flow. And so it immediately confirmed to us that, yeah, this event-based vision has a promise for us, for our drones. So the second thing then we said is, okay, we want to get rid of the conventional processing. So we want to use spiking nets, which go nicely with the events, of course. And this was published in 2019. And we took a spiking net. And I think the cool thing is that, yeah, at that time, it was a very complex task that we did. And it was also, it's unsupervised learning. So we're not doing, backprop or something. We were doing, we made a modified version of STDP, and we used unsupervised learning in all parts of the network. Let me indicate that. So you have the inputs on the left, it's the on and off events. Then you have the SSConf layer, and with this learning rule, it would learn textual features. In the MSConf layer, it would learn local optical flow. And the cool thing is it was the same learning rule, but I will show you soon why it would learn flow instead of textual features. And at the end, we did some pooling and then a dense layer. And this learned global flow field properties. If you look in flies, there's the lobula plate, and there's neurons there that respond to divergence or a lot of flow to the left, like to global optical flow field properties. And actually in our network, we had such neurons in this dense layer, all with the same learning rule, but the differences were in the structure of the network. So for example, in between the SSConf and the MSConf layer, we had connections with different time delays. And this is very similar to the elementary motion detectors in insects. And with the learning rule, different neurons would learn different types of flow. And I can show you that. I'll also tell you, like in this network, we had like 100K neurons and 2 million synapses. So I tell you this because later, actually, we put a vision network on board, which was much smaller. These are the results of the learning. So on the left, you see the input, and on the right, you see the first layer. You see that it starts very vague, but as we present more and more events, you see these features arising, like contrasts, different orientations, etc. And then we show now the MSConf layer on the right, and we color code the local flow. So you see this input is this turning wheel, and you see on the right that actually this MSConf layer learns optical flow, local flow, and it was working really pretty well. So I think
question, Guido. How did you structure this so that it was unsupervised learning, learned these features? In other words, what was the loss function, or what was the, how did it know that it should, you gave it at the end, the global flow, or in what way did you get it to learn these features?
Yeah, it was completely unsupervised. So, so there was no, at the output, let me go back a little bit. At the output, there was no target. So let me get here the, So here you have events, and then this is a convolutional layer. And these events, it's like, the green and red kind of edges. And the way you should understand this learning rule is that it's just clustering. And so it's going to find, if you often see a vertical edge and then like a horizontal edge, so vertical and horizontal, it's going to learn a cluster for horizontal edge, a cluster for a vertical edge. If you see a contrast often, like on and off, it's going to learn that. And so that's why here, so that's why here you learn textual features. But here, we actually merge all those activities. And the only goal actually of these textual features was to get rid of noise. So we merge that. And what we then see is, basically edges moving over the image. But between this layer and the MS-Conf layer, we have delays. So a fast delay, slower delay, etc. And if you cluster that, some things, go very quickly over these. Quick motion will only visit some delays, and a slow motion will visit all of them. And then if you cluster that, then you basically will learn, slow and fast motions in different directions. And so it's a structural change. The learning algorithm is unsupervised, it's just clustering. But because we add these delays, it will learn optical flow, local optical flow. And here at the end, we pool all of this. So we do some kind of pooling, averaging, let's say. And then basically what you get is that if in one of these channels, like the motion to the right, a lot of our things are active and you just average that, then there's one neuron that's sensitive to motion to the right, to that channel, is going to be very active. It's also clustering. And so it will cluster general motions, like slow to the right, fast to the right, slow to the left, fast to the left, etc.
Okay. Thank you.
Yeah. But it makes it very hard. We have a benchmarking fetish in AI and computer vision. And so, local flow arises, but not necessarily, it's very hard to match to a ground truth because we're not doing supervised learning. And so it creates some problems. Actually, in a follow-up study, we did something different. We did self-supervised learning. So this is a different setup. Sorry, I'm going to go hugely over time, I'm afraid. How long do we have?
You have about 15 minutes at least, right?
Okay.
More like, is that correct? About 15 minutes for sure.
Okay.
Is that
Cool.
okay?
Yeah, I'll try to speed up a bit. Hey, so here we have a different setup. So we don't have supervised learning, but we have self-supervised learning. And so what happens is we have events coming in. We chop them up in very small slices. And so we make very tiny time windows. If you just use one time window and a feed-forward neural network, a traditional one, then you cannot get flow out of this. And so the reason we did that is we want to go to a spiking net. Ideally, it should get events asynchronously. And the best way to approximate that was with very tiny time slices. And so the network needs to have a memory to remember what it saw before in order to estimate flow. And here we use a spiking net with a kind of UNet structure to predict flow. And then we use this flow on a longer time scale and to take a long event window and to what we call deblurring. I don't know how how familiar everybody is with that, but if you accumulate events over a long time window, you're going to get an image like this, which is pretty blurry because the edge moves. You have a long time window, so if it's moved like 20 pixels, like this green thing here, the blur will be 20 pixels. But if you perfectly know the optical flow, then you can go to the events at the end and you're going to transport them back to the start. And if you do that well, then you can get this very sharp event window image. And so if you do optical flow well, then you can deblur this event window to make a high contrast image. And we call this self-supervised learning because you can calculate an error here, like how good is this image? How sharp is it? If it's not sharp enough yet, there's some errors, you can backpropagate that through the network. So this is self-supervised learning because we don't need any ground truth optical flow. We just make, we record events with the camera and we apply this framework, and you can learn in any environment without any ground truth, but it will learn optical flow very well. I only show this because this is has a much higher performance in the flow determination. It's also a bigger network. It had like almost 4 million neurons and 1 billion synapses. So yeah, it's pretty big. I'm gonna speed up unless there are questions, of course. So what we then did is we said, oh yeah, we should also do control. So we replaced this simple control law with a small spiking net. But this is a dirty green box, so I'm only going to talk about the nice green box. In 2021, we published this as ICRA, and we used the Intel Leugering chip for the first time in the control loop of a flying drone. And it was doing these optical flow landings. So what was it doing? We were using a traditional computer vision pipeline to determine the divergence. And then this optical flow divergence was encoded in spikes. It went into the Kapoho Bay. And then this network we trained, it outputs spikes, and then this gets translated to a thrust command. So this is the network. It only had 35 neurons. We did a number of things. So we evolved this spiking net in simulation and then transferred it to reality. And we did a number of things to cross the reality gap. But it's like a zero-shot transfer. So if you set up your evolution well, this transfers immediately to the drone. And in this experiment, we were only doing the vertical axis with the Leugering. So and this is the experiment. So for us, it's quite a big drone because the Leugering had to be connected to an upboard, which is pretty heavy. But you can see the optical flow landing here, and it was looking really pretty good. But yeah, this is only the control part. And the control part, like I said, yeah, it was 35 neurons, but it's also not our main problem, right? So what I want to present to you today in the last 10 minutes or 12 is fully neuromorphic vision and control. After, I think working on this for 6 years, we finally did this. So a fully neuromorphic vision and control pipeline. So we have event camera events coming in, and then we have a spiking net, and then we have low-level control commands coming out. So that's what where we're now at. And here I show a little bit of details of the spiking net. So I'll explain to you that we're looking not at the full field of view of the event camera. We're only looking at 4 corners. This has to do with limitations we had on the Leugering. And this is the brain. So here we have actually, I'll show you that in a second, we have 4 parallel spiking nets that for each corner, they estimate the optical flow. So this is for the top left corner, the top right corner. And what you can see are the neurons. So if they're spiking, they're white. If not, they're black. And you see here the second layer and the third layer, and then, the output layer. That's actually generating the control commands. So yeah, our main challenge was, how do we learn a single spiking net to do this, right? So, and the first thing you may think of is reinforcement learning. And we do end-to-end. But yeah, to my knowledge, this is difficult because you need to generate events. And for example, this is a study from 2023. They made a data set of events. Basically, they make many images and with very short time steps. And then they use that to generate events. Yeah, you can do that for a data set. It's already a lot of time. But if you need to do this for reinforcement learning, then reinforcement learning itself already takes a long time. But if you then need to, per millisecond make an image, or even more than a millisecond, then this becomes basically prohibitive. So end-to-end reinforcement learning with events, to us seem prohibitive. If there are other opinions, I would love to hear them, of course, in a discussion. So what we did instead was to split vision and control. But how do you do this? And so yeah, we did it as follows. So we assumed a camera that would look down and it would look at a flat surface. And so that's simplifying our task. It's also what most drones do when they control their velocity. And so this is our floor. If we have an event cam, it will see something like this, these events over time. It goes into a spiking net 1, and it outputs 4 optical flow vectors in the corners of the field of view. Yeah. And then 2, we would learn the control in simulation. And so we have FlightMare here. So there's a drone, and we know the ground truth velocity of this drone and also the rotations. Knowing this, and also the height, knowing this, we can, perfectly say what the flows should be in those corners. And then there's a second spiking net that maps these 4 flow vectors to commands. And so this is how we split it. Now, this is a little bit of details on the vision net. So, oh yeah, let me get the laser pointer again, sorry. So here is events in one of those corners. So it's 32 by 32 pixels, and there's on and off events, so 2 channels. And it goes through this encoder, pooling, and then you have, we decode this layer, we decode it to a floating point value for the horizontal and the vertical flow. So if you have all 4 flow vectors, and you know that you're looking at a plane, and then you can, basically those 4 flow vectors, they define a homography. And so you can basically predict dense flow for the entire field of view. Now, and what we can then do is the same trick we did before. So we do self-supervised learning, and we have a big event window resulting in a blurry image. We have the network predicting flow, which predicts dense flow actually. So we can derive a dense flow field from this. And then we can deblur all the events and look how sharp this becomes. And we learn the full network with this deblurring. So we actually took the event cam from our drone, moved it in our arena, gathered data, and trained the optical flow estimation with this, without any ground truth. And this prevents a reality gap at the sensory input side, because we learn with true events. Now the problem comes, like in simulation, you can learn how to map these flow vectors to control, but how do we link these networks together now, right? And so let me, And so the vision network receives spikes from the on and off events, and the penultimate layer is still spiking, and it's decoded to floating point values here, right? So far, so good. This decoding is a learned decoding. Then the simulator has a ground truth optical flow, which we encode with the learned encoding to input currents for a spiking net that is then also decoded to the control commands. The problem is, so it seems logical to do like, okay, we have input spikes, we have the vectors coming out, and we throw that into the network anymore, again. But in neuromorphic hardware, you don't want this part, the floating points here in the middle, and you don't want them, and you cannot do it, for example, on the Leugering. And so what we want is actually to connect these 2 together. And it took us, I don't know if we're stupid, but it took us quite some while to figure out. And so what happens is, we have the spikes outputs from the first network. We have a linear matrix to map the spikes to the floating point values. And for the encoding, we actually take floating point values, and we have a matrix that maps that to input current. And so actually, because this is a linear mapping, and that's a linear mapping, and you can combine them, and then actually you have your weights that map the spikes of this layer to the current input of that layer. And so this is how we could develop vision and control separately, and then actually just merge them with this simple operation. And so this is how we link them together. And this is what our hardware setup looks like. And so we have the event cam, it goes into a upboard, like I said. These events are then sent to the Leugering, and then it sends spikes back, and this goes to the PX4 control board. So there's low-level control commands. These are the events from the corners of the field of view. They go into the spiking net, and this is decoded to the low-level control. And I'm going to show you some videos how it works. Oh, there's a lot of sound here. Perhaps I should switch it off. So this is the drone. It's doing one of the most difficult tasks. It's hovering. So why is it difficult? Because if you hover, you have no events if you do it perfectly. So this is actually difficult. You see it drifting a little bit. Here you see the events. Here you see the spiking net activations. And it's drifting a little bit, but yeah, I think it's quite acceptable. And what you see next is when we give a forward flight command. And so it flies forward. You can see already here that the events move. I hope you see my mouse, that they move already a bit backwards. And so it's controlling the forward motion now. And so we're not doing landings, we're just moving into different directions. And so I'm also going to show you a little bit faster. Like, I'm not going to show you the whole video, it's a bit boring, but look how these events get already a bit faster. That's the thing we're controlling now, basically, this flow. And this is the network, spiking all the way through to the low-level commands. Oh yeah, I'll also switch off the sound here. So this is with lighting. So this is a normal landing. And so again, the divergence is used here, and we send a set point. But now we also, screw with the network, switching it on and off. And you see that, yeah, the events are flooded here, but still it can land. This is in relative darkness, and yeah, it has enough events to land. And then we also try it in pitch dark almost. Yeah, then I must say it just crashes. So that doesn't work. Don't tell Intel that their Leugering was on there. No Intel people in the audience, right?
No, I don't think so. Maybe.
Okay. Yeah, it didn't break, by the way, so that's good. We protected it very well. And this is a little bit more complex. Oh yeah, I don't know if the video's running. Yeah, so it's gonna fly a square. And so you can basically now the drone can choose to move into any direction here. And so yeah, we also made it like do a frisbee experiment where it was like going to the front and also yawing. I guess it's a little bit later in this video. Let's see if it's here. And so I think it's gonna do this perhaps. Let's see. And so it's gonna fly and turn around in the same time. And we don't often do that with these experiments, with these, with normal optical flow, because you typically don't like rotation. It's pretty quick, but yeah, with the event cam, you can easily do this. This is what it looks like, the performance. And so a little comparison quickly. Oh, I'm trying to get my laser pointer. Yeah. So this is what the simulator looks like. So if you want to move sideways with a flow of 1, then you can basically do that. In reality, the faster ones it cannot really make. We had like this is the full network control. And this is a PI controller. So here we do the vision with the spiking net, but the control with the PI controller. As you can also still see that, even a simple PI controller, it's not so easy to realize with the spiking net. The PI controller actually does better. You see that, it actually, does the control very well. And so, like if you want -1, you're going to get there basically. And so, and this is what we wanted to test, like how much energy do we use? I'm gonna highlight one thing here. I should have kept the laser pointer, of course. But so this is a Jetson Nano. So of course, energy comparisons are always super tricky. And so there's like the idle energy, which is not so different actually, what we measured on Nahuku 32 and the Jetson Nano. But if you look per inference, we see a huge difference. So yeah, this is really very power efficient compared to the Jetson. And also the inference speed. And so this is when you have lots of motion or lots of texture. It runs at 270 Hertz. But it can also, if you move slower or have less texture, it runs at 1600 Hertz, which is very, very fast. And so, and it uses even less energy for inference. While on the Jetson, yeah, it always runs at 25 Hertz, basically. And so to us, yeah, this shows the potential, you know, that's there. So that's the conclusion. So of course, we're improving this. We want better control. We want, you know, we're just doing motion control here, but there's so much more you should do with the drone. But the conclusion to me is that it's a huge promise to realize insect-inspired autonomous flight for tiny drones. And this is the team. So yeah, we have Federico Paredes Baez, Jesse Hagenaars, Ingfu Xu, Stijn Stroobans, and Julien Duperroux. They worked, this is the team of the fully neuromorphic project. And there's other people that were involved in the earlier projects I showed. We also work together with Sander Boté from the University of Amsterdam. He's like really expert in spiking nets. And if you want more information, then please go to our website. And yeah, I would, of course, be super glad to take questions.
Okay, good. Thanks a lot. So Garrett has a question. Maybe I'll relay it. I think he can hear you clearly, right?
Yes, so this was great, fantastic demonstrations. Now, your drone was doing really well on this flower field with high contrast, very busy, right? How would it operate if there were some regions with very low gradients, let's say a beach or something?
Yeah, so we did this carpet on purpose because we didn't want to, you know, tackle in this article the texture problem. And so, to be honest, so under the carpet is a grass carpet, which is more natural already. If I use the CMOS setup, I can actually fly over the grass carpet. We didn't do that test yet with DVS. Actually, we're going to do it now because this paper has now been reviewed. And obviously this question also came. I'm not sure the resolution is good enough because there's like very fine grained texture in the grass. I'm not sure the DVS will pick up on that well enough. So we're going to test it. We're going to do it in a tethered setup so that it doesn't crash. And we're going to see how much texture is necessary. This being said, you know, insects also have quite low resolution. And like honeybees are known to drown in lakes. If it's like a very sunny day, no clouds, they're above the lake, they see very little flow, they actually go down and they even go into the lake, they even drown. And so if you have no visual texture, like really a completely white floor, that is problematic for visual solutions. And so, yeah. But typically, in most real-world environments, if you have a very broad field of view, you have texture somewhere, and then it's typically enough to keep flying.
Another question over here.
Yeah, so in that slide on energy balance or the energy estimates, you had microjoules per inference. Do you know how many floating points or individual instructions are used for each inference?
How many floating point instructions are used for
Each inference?
For inference in not on Leugering, but on the CPU?
Yeah, or integer instructions. I mean,
On the Jetson Nano.
Yeah.
What was the inference rate, I guess? The max per second, right?
right, something like flops per second.
Yeah.
Or integer instructions per second.
Yeah, we were running the same network. So, I mean, the inference speed was 25 Hertz. How many flops I would have to, I would have to calculate. I don't know by heart. I know we had like 28K neurons in the network. Yeah, I could get back to you on that. I'm sure. And so it's a pretty small network in the end. And one of our challenges was to scale down the network so that it would fit on the Leugering. And so Leugering can actually have more neurons, but then you need to go down in your weight resolution. And so I think they even say 1 million neurons, but then you have binary weights. And so if I remember well, we had 8-bit resolution. And so it's a tiny network. So yeah, I can get it. The thing is that you cannot really do a very fair comparison in the sense that we ran the same network on the Jetson Nano. It's compared to normal deep nets, it's small. But for example, we were running it as a spiking net. So we were doing a lift neurons. Yeah, would you do that if you use a Jetson Nano? I think not. You know, so perhaps there's some overhead there you could get rid of. So if you want to compare the best solution on the Jetson Nano with the best solution on the Leugering, you would not run this network. But yeah, I think it's more indicative than, yeah, you know, a final comparison.
Okay, thank you.
There's another question here, in
Hi, Guido. Amazing work. Thanks a lot for the talk. In this question of the weight resolution, you've mentioned 8 bits. Was this like the let's say lowest resolution of weight that you needed to perform this task, or?
Yeah, was 8 bits a choice of the hardware, the Leugering hardware, or was it intentional on your point? Because Jetson Nano supported it. Yeah. What set that weight resolution? Is that right? Weight precision. Weight precision.
Yeah, so it's all about the trade-off between like accuracy and so it doesn't. If you go to 4 bits, you know, it could still work, but accuracy goes down. The same goes for like yeah, choices on the network size. Also, when we made the step from because you could also say instead of looking at 4 corners of the field of view, you take the full field of view, but you do either a big stride or you do pooling of the inputs or something. Like you could make different choices. Like it's a pretty big design space in which we looked for a very efficient solution that still gave a reasonable accuracy. And you also don't need, like we're not doing odometry and that you need to fly 200 meters and have 5 centimeters resolution. We don't care. We roughly want to see the velocity of the robots, basically, the flow. But yeah, it's all on a trade-off. So 4 bits, it will still work. And we were definitely constrained by the Leugering. So a big part of what we did was to actually get a really close model of the Leugering, so that we could, you know, train our networks with the same kind of settings, dynamics, like how our layers updated. Yeah, there's many choices like thresholds and, you know, yeah, there's many details that I don't even know, to be honest, because Federico, that was a part he dove into, but that was a huge part of our effort. Yeah.
Okay, good. Thanks, Guido. I think we better wrap it up because we're at the hour point, and it was really nice talk. Really enjoyed it a lot. It's very right in the core of the workshop. And maybe you're interested in joining the Slack of the workshop so people can ask you further questions. I can show you the Slack link. Is that a good idea? Yeah. And then perhaps you could also, since you had a really nice set of papers, which are going to be in the video, but they're going to be a bit hard to access. If you can extract that list of papers, also put it on the Slack. The links to those papers so people can read further about the work.
Perfect. Yeah, great. Yeah.
So fantastic. So hope you can join us here, and we miss you here.
Yeah. I'm very sorry I couldn't be there, but have fun there. Looks great. Bye-bye. Have fun.
Hey, everyone. Thanks for being here. I'm Felix from SpiNNaker. I'm going to give you a hands-on tutorial on, first of all, training an SNN with one of our in-house libraries, Rockpool, and then deploying this SNN on this guy here on a Xylo audio dev kit. The main purpose of this is that you get an idea of what can be done with our chip, how it can be done, and hopefully to motivate you to approach us and to to try doing that by yourself as well for some cool project. Maybe as a, yeah, no, okay. I will basically, so I guess you all were yesterday at Jason's tutorial on training in SNN. I found that really nice, and I decided to more or less pick up where he stopped. So we now all have an idea of what is an LIF neuron, how we can train SNNs in different ways. And one way that Jason particularly focused on was backpropagation through time. And this is also what we will be using here. All right. So instead of SNN torch, this time we will use rockpool, just because it's the library that we use for, in the end, deploying models on our chip. So I suggest let's start directly with that one. What can you do in rockpool? You can define a network, you can train it, especially SNNs. And then from there on, you can go through all these steps that you might want to do in order to deploy the model on our hardware, which means you can extract the computational graph from your model, make sure that all the specifications that are necessary to be deployed on the hardware are generated correctly, that the parameters are quantized, and then you can actually deploy it on the hardware and interact with the hardware live in real time. If you want to know more about this library rockpool, you can visit rockpool.ai. You will find instructions there on how to download and install rockpool, but also a really large base of tutorials on how to work with it, how to use our hardware, an overview of the hardware that can be used with that. So it's quite exhaustive, and it's really helpful. The idea is to make it as easy as possible for anyone to use that. So that's how the docs look like when you visit rockpool.ai. Maybe one small detail regarding the neuron model. If I remember, oh yeah, you have a question.
So just very on the outline. So your approach is not to train and being aware of the quantization. Just training floating point and then you quantize it.
There's different ways. So yes, we since recently we also support quantization aware training. It's a somewhat new thing, new feature. I won't include that in the tutorial here, but it's possible and it's supported. Yeah, one small detail about the neuron model. I think so there's always many different versions of all kinds of neuron models. We had a nice discussion on that over lunch. So we will be using a leaky integrated fire neuron model. If I remember it correctly, Jason, in your case, the input was basically projected directly onto the neuron membrane potential. In our case, there will be some synaptic dynamics in between, which means we have the actual input to the neuron, which might come from the outside or another neuron, which is scaled with the weight. And this actually drives a synaptic current, which is basically an exponentially decaying signal that jumps up whenever there's a spike in the input.
Yeah, so functionally like a pair of what losses.
Exactly. It's two low pass filters in a chain.
Delay, right?
Yeah. And so from there on, the rest is exactly the same as yesterday. You have the synaptic input, this I here, that then drives the neuron membrane potential. And you have the spike mechanism, meaning that whenever some threshold is exceeded, this threshold value will be subtracted from the membrane potential and the spike will be emitted. So we're doing a so-called soft threshold. We don't reset to zero, soft reset. We don't reset to zero, but we do subtraction. All right, so let's get our hands dirty and code. I think there is a link on Slack on how you can access this Jupyter notebook. So if you want, there's one version called Xylo SHD Demo Live, where you can code along with me. But there's also the full version called Xylo SHD Demo Complete, with all the code already filled in. If you just want to, read along or look up some specific.
It's in the general channel.
Yeah, so it's in the general channel. Thank you, Gregor. Okay, so what are we going to do in this tutorial? We'll first have a look at how does a leaky integrate and fire neuron or model, how can that be instantiated in Rockpool? How can different layers be combined to a whole network within Rockpool? And then we'll apply this to an audio task by training on the spiking Heidelberg digits data set and deploy this model that we train onto the hardware. So let's get going. This is just some setup. This might take a bit longer on your machine if you're coding along, because it might have to install some of these libraries that I have already installed here. Okay, let's dive straight into Rockpool. So first of all, we need to import it, of course. So we do from rockpool.nn. So some of you, those who use PyTorch, might notice it's a bit inspired from that, this NN part, where NN is everything that's kind of related to deep learning. And then module is kind of the is the package that contains different modules. It's again very similar to PyTorch. So each module is some entity that might be a layer or actually a whole neural network that then can receive input and produce an output. So it's really strongly inspired from PyTorch. Okay, and what we will import is the LIF class, leaky integrate and fire. Okay, so now we will instantiate one leaky integrate and fire layer with just one neuron to start here. So, and to specify that there's just one neuron, we just set the first argument to 1. For more neurons, you would obviously choose a different number. And then we can specify further parameters such as the time constants, the threshold. We will for now just do the threshold. Okay, and we get one LIF layer with shape 1, 1. So this shape means you can optionally include a set of weights here, and then you would have a 2-dimensional shape. But let's ignore that for now. We will keep it simple here. Okay, let's just generate some random input, just like Jason did it yesterday in his tutorial, just to make sure that our live neuron is doing the right thing. And in order to run this input through our neuron, we can just call our live object with this input. When you do that, it will not only return the output, the actual output, it will also return a second object, which is the state. So it's the state of this neuron, including membrane potential, in synaptic current, as well as optionally a dict, which includes a recording over time over these state variables. So if we want to have a clear idea of what's going on inside this neuron, we can specify to record this by setting record equals true. Right? So let's see what's the output of that neuron. Okay, it's just one single spike in that case. Now if we look what did we actually record, we have IREC, so that's the recurrent recurrent synaptic current. In our case, that's not really existent because we don't have any recurrent connections. We have the spikes that this neuron produced over time, the synaptic current, the VMEM, and I'm actually not quite sure what this view here is. So let's just plot the most interesting ones, which is the synaptic current and the membrane potential. And we see here, synaptic current is in blue. We see it jump. There's a few points where it jumps up. That's when there was an input spike. Seems like our input was rather sparse. And whenever this is happening, this synaptic current drives the membrane potential up. And then here it actually reached the firing threshold, which I set slightly high. So here it actually fires, it is being reset, and then it continues being driven by the synaptic current. It almost spikes here, it looks like it just missed the threshold by a small amount. And then here again, we have this input spike that drives the synaptic current, and then as a consequence, the membrane potential. I don't want to go into details too much about the leaky integrated firing neuron. It's more in order to show you what you can actually monitor with ROCpool. Okay, so now all ROCpool modules have a range of different attributes. One of those is the current state. So this is also what has been returned in the previous forward call that we did, which we ignored. So if we just do live.state, we get the state. So currently in the previous time step, there were no spikes, and the ISIN and VMEM had these values. So you can read it out that way. Another important attribute is the parameters. And this includes all the trainable parameters. So this might include time constants if you train them, synaptic, so membrane and synaptic time constants, the bias, and the threshold. There's also the so-called simulation parameters. That names, you will see in a second where that name comes from. Yeah, so it contains basically non-trainable parameters, of which usually those simulation parameters as the time step, or some others, such as in here we have, for example, a limit on how many spikes can be generated, or some arbitrary noise that can be injected. In general, the name might be a bit confusing because this is just any parameter that is not trainable. We will see that later on. We can specify, for example, that we don't want to train our threshold. And if we do that, this threshold will not appear in the parameters here, but in the simulation parameters. Are there any questions so far? Okay, so then let's have a brief look at the spiking Heidelberg digit data set. So it consists of spoken digits, both in English and German. They go from, I think, 0 to 9 or 1 to 10, I'm not quite sure right now. But so it's 10 for each language, so in total 20 different classes. They were pre-processed with a very precise and complex cochlear model, and thus converted into spikes. And I'd say it's a quite common data set for audio benchmarking in the spike domain. I don't know who has heard or worked with this data set before. Okay, yeah, a handful of people. So if you haven't heard about that data set, don't worry, it's really just a spiking audio data set. What we will use in order to feed or to load our data set is Tonic. We have a very prominent Tonic developer in here. So if you have any, so it's actually, I think it's been mentioned a few times already. So Tonic is actually, it was born here in Telluride. And of course, if you have any questions about Tonic, the best person to talk to is probably Gregor. Yeah, so it's a tool that made data loading for spiking data much easier, but not just loading, also transforming data set is it's super nice, super useful to do that with this library, and that's also why we're going to use it here. Let's get back to the code. I don't want to go too much into the details of how to use Tonic, and so I will skim a bit over these next two cells. Basically, what we're doing is we import it. We define a few data set specific parameters. The nice thing here is that Tonic can take care of downloading this data set and setting it up. So if you're following along, coding along, probably when you run this cell, it should download that data set, which might take a while, so maybe skip that cell. I have downloaded it already, so Tonic realizes that and then doesn't download that again. So let's just have a look at one data sample from that data set. So what we see here is a raster plot of the spikes over time. So times the horizontal axis, and then the vertical axis corresponds to different channels in which this audio signal was encoded. And you see it's quite a lot, so it's more than 700. So that's quite a complex, quite a refined representation of the audio data. And it sort of kind of looks like a sonogram. Yeah. So for our hardware, we don't support 700 input channels. It's a bit less than that, 16. So we will have to downsample that data a little bit. And there's Tonic for us to do that. So I just combined a few transformations here. So the first is to downsample this data. And then since we're working on a von Neumann architecture, we generally don't work with events, but rather in time steps. So we have one transformation that arranges these events in a raster or in a series of frames, so that we basically bin our events in time.
I have a quick question.
Yes.
This might be a very good question. I forgot. How's your data downsampling? Is it by dropping channels or by averaging channels and bins?
It's by summing them, right?
Some.
So you multiply, you specify these factors, and then you just multiply all of the channels with that factor. So it's just really like it's multiplying for
mean.
If previously your highest channel was 700, and you say my factor is 0.5, and it will be reduced to 360.
Yeah, how those like true channels averaged out to give you frequency.
I see. So no spikes will be dropped. No. So it's literally just like for every event, changing the channel index, and that's it. So there's no operation across events.
Gotcha.
Yeah.
Okay. So if you have a pair of spikes happening at the same time, then it's something wrong.
No. This doesn't do it.
Sorry.
So in the okay. So then if you go to the 2 frame as well, then they will be added.
Gotcha. Yeah.
Yeah.
So basically, after this one, we have channels that are not necessarily natural numbers. So we do.
Yeah. So they will be truncated to integers.
Okay.
Yeah. And then in 2 frame, what you do is count for each bin. This is basically a counting operation, so adding up. So, does
Thanks.
that answer it? Or?
Yeah.
Right. Yeah. So the last 2 transforms are just some. Well, first of all, bringing the data actually into a tensor. I think before that it's probably a NumPy array, and then just some reshaping to have the. It's actually a cropping. So yeah, I think it looked. Yeah, we're cropping the first few at the last few milliseconds of each sample, so that they all have the same time, which in this case is 250 milliseconds. Anyways, I don't want to go too deep into the data wrangling. It's not so essential here for this tutorial. Okay, so now let's set up the data set with the transforms that we just specified and take another look at this sample that we looked at before. Let's plot that again. And you see it's a little bit less, that the resolution has decreased a little bit. That just comes from the downsampling. But as you will see, it still works.
And here one spike could be is actually now could be more than one, right?
Yeah. Oh yeah, yeah. Just by the way, it's plotted here. Yeah. Okay. So another thing we will do, maybe one thing that I should point out. Maybe let's do this right here. Let's take a quick look at the architecture of Xylo. Xylo supports up to 16 input channels, and then those can be projected onto up to 1,000 hidden neurons. Those hidden neurons can be rather freely connected recurrently. This also means you can set up this set of recurrent connections in such a way that you get a feed-forward network out of it, for example. So this is not necessarily meant to have a recurrent neural network. Can also define your connectivity matrix in such a way that you get a feed forward, and we're actually doing that to some extent here. There are 8 output neurons. We can read out the states and spikes of all of these neurons. So in theory, you could, you don't need a specified set of output neurons from a more scientific perspective. However, those are a bit easier accessible from the outside, just when you want to interface the chip in a specific application, then it's easier to just use these 8 neurons. Okay, so.
And sorry, you can control the precision of the weight.
Well, so there is a fixed precision. The weights, do we have that here? Yes, we have that here. Perfect. So the weights have 8 bits. The state variables have 16 bits each. And
sorry,
yes.
State meaning, for instance, the time constants of the
currents and so on. Yeah, exactly. So those are just the state variables, not the parameters like the tau or threshold. For the taus, so maybe I should also briefly dive into that here. We are approximating an exponential decay in terms of a bit shift. This is computationally just more efficient. And for this bit shift parameter, we have a 4 bits resolution. So for the threshold, we also have 16 bits. And for the connectivity, each neuron has 16 pairs of 2 input synapses. So that means you can define, so these pairs, what I mean is you can define 2 different synaptic time constants. And then for each time constant, you have 16, you have a maximum fan-in for that neuron of 16. However, if you don't care about having different time constants for your neuron, you could also just set them to the same value, and then effectively you have a fan-in of 32. Yeah.
Do the weights have a sign bit?
Yes, they do.
Is that included in the age or?
Yes.
Okay, cool. How flexible is it this shift? Okay, so you're able to specify the values when it's normalized between 0 and 1. Letting the increments of 6.06 through 5. So
the bit shift works as that. You maybe Sadiq can explain that better. Yes. Yeah, we don't have a whiteboard here, right? So that, you know.
Does it shift and subtract?
Yes. And so what you can specify is the amount by which you shift. So, okay, maybe I try to explain it. You have your membrane potential, you bit shift that. So basically one shift means a division by 2. And so depending on how often you apply this shift, so assume we just shift twice, we divide our Vmem by 4. And this new value is going to be subtracted from the original value. So then effectively, yeah. Okay. So we have the new Vmem is the old Vmem minus 1/4 of that. So that's 3/4 of it. And so effectively our decay factor would be 0.75.
Does that mean that you can also subtract the entire membrane potential at once?
Yeah, you could. Yeah, it should, yeah, if you just don't shift, yes. I think 0 is permitted, and yeah, I don't know what you would get out of that, but yeah.
This then it would be like a binary.
Yes. Yeah. Yeah. All right. Are there more questions to the hardware architecture?
So the longest time constant you can set is then 2 to the 4 time steps. Where it would be like there is a decay constant.
Basically, yes. Yeah. So
4 represents 16, so it's 2 power 16. So it's there's 2 to the 4 number of distinct time constants that you have. So but they're exponentially spaced. So because we have 16 bits, right? So we can do 16 bits. But you only have 4 bits for the
So
that 4 bits represents the number that will be used to bit shift.
Yeah.
So that's 16 essentially is how many you can do maximum.
or 15, and then
I see. Okay, yes.
Yeah.
Right. You cannot shift at most by 4 bits, but you can have 4 bits to specify by how many bits you shift. So yeah.
Yes. Okay, now maybe if we really want to go into the details,
That's fine.
okay. Okay, then I will. Okay.
I mean, essentially, that's just a simplified version for fixed point arithmetic to do exponential.
We do a shift that down.
Sorry?
Can we do a shift that down? No.
We already ate our potato chips.
Okay, let's go back to code. Let's get serious again. So as I mentioned, there is only 8 output neurons. Yes, you could in theory just use any other neuron as well. In principle, but we will stick with these 8 dedicated readout neurons. And so we will just classify 8 different classes of this data set and not just and not the full 20. So we'll actually just look at a subset. So we will write a small data loader that just loads the first 8 indices of that data set, the first 8 classes. Really, it's not so relevant exactly how that works. It's really just a standard Torch data loader. Okay, or data set actually. So the data loader is also from Torch. We specify a few options, such as batch size will be 128. We'll shuffle during training, but yeah, so those are actually quite standard procedures. Torch data loader, we don't need to really dive into that. Let's rather have a look at our network. Okay, we need to wait for the data loader to be ready. I assume it's currently applying the transforms, which takes a few seconds. Okay, here we go. So this is a schematic of the network architecture that we want to deploy. We have our 16 input channels. Those are the ones that we downsampled from the data set. We pass them through a first set of weights, 16 by 20, and then we project it onto 20 LIF neurons. From there, we basically have a multi-layer perceptron. So we go on with another layer of 20 LIF neurons. And then finally, we have our 8 output neurons. We add a residual connection here. So who has heard of residuals before? Okay, not everyone, most of you. It's basically a trick from standard deep learning, where they realized, okay, when we have these connections where basically one or some of the layers are skipped, we have a bit a more efficient flow of gradients in the backbord path through those layers that are further away from the output. The cool thing is about Xylo is it supports that in a very interesting way. If you remember, I mentioned there is up to 32 input connections for each neuron. If we assume that we have all-to-all connections between each of these layers, and we look here at our at the inputs to our 8 output neurons, we have 20 neurons here that connect to them, but then also those 20 neurons here that take this skip route here. And Xylo has some nice addressing scheme. So if you add up the number, that makes 40. So that would actually be 8 too many. But in case of these residual connections, the addressing scheme allows for this to happen. So basically, because here the weights are shared, so both of these pathways go through the same set of weights. This makes this possible. Yeah.
Does that mean that if it's producing spikes,
Mm-hmm.
then you produce like 2 spikes or 3 spikes at a time? Does it mean one is coming from the 2 layer and the other one from the 1 layer?
It can. So it doesn't have to. So if this guy produces a spike, this spike will be routed here to that layer. But then also going this route here will be routed to the readout neurons. If these layers and these layers produce spikes simultaneously, they will just be added up. Yeah.
Is this diagram, is this the particular network that you're doing right now?
Exactly.
Okay, but in general, it does support a recurrent connection.
Yeah, you could add recurrent connections, for example, here for this hidden layer. Exactly, as long as you take into account the limit of fan-in, you can basically have any architecture that you want.
Question about the hardware. So all of the neurons are processed simultaneously, so it's a stepped operation, I assume.
Well, yeah.
And all of the spikes are, so in principle, you can route, if every neuron wants to broadcast to 32 other neurons, in principle, it takes longer, or is the clock speed fixed?
Clock speed is fixed.
And it's already, okay, so it's because in VE, they have this approach of this like barrier synchronization and other stuff. So for you, it's like the clock speed is chosen so that
also do that. You're talking about the accelerated mode where if you're done with the processing, then you go on to the next step. You can also do that.
Okay, so you have the 2 options. Okay.
Plus, maybe that's also, since you bring the clock speed up, you can also set it manually. And so then if you think back at this bit shift decay, you can actually specify what that means in terms of time constants. You can actually you can choose between a rather fast dynamics or rather slow dynamics by setting the clock of your chip. Okay, so let's set up this network. We'll import a few rock pool modules that we use for that and define a few parameters. And now to set up this network, we will use the sequential combinator. So this is really, again, it's very similar to Torch. It's been done intentionally that way, that when someone is coming from PyTorch and wants to start working with Rockpool, it's a really easy entry. And so we use the sequential. Just note that we imported that from Rockpool here, and so it's not the Torch sequential that we're using here. It just works the same way. Okay, what have we here? So we first have a linear layer. So there's this set of weights. We use Torch as backend in this example. So we use a module that's called linear Torch. And here we specify how many channels are coming in, 16, how many are coming out, 20. So it's a 16 by 20 matrix, basically. As a side remark, here we're using Torch as a backend. There are other backends that are supported in Rockpool, such as JAX. So if you're more comfortable in training your models with JAX, this is also possible in Rockpool. Okay, the next object in our network is the actual layer of leak integrated fire neurons. We have 20 live neurons here. So we'll just do live again with Torch as backend. So live Torch. Neurons. And now we have this residual block here. We don't need to bother ourselves with how is this routed, what is added up. We just import a residual connector and specify this here. And in there, again, we have a weight matrix, the linear layer. This time it's 20 by 20, and then 20 LIF neurons. So linear Torch, 20 by 20, and live Torch 20 neurons. Let's close the residual block and finish the network by adding our set of 8 output neurons. So that's another linear layer, 20 by 8.
You need a comment, right?
Yeah, thanks you. Someone is paying attention here.
Made a lot of mistakes.
And our 8 LIF neurons. Here we go. Let's see if that worked. No. Oh yeah, I have to put these into brackets. Let's give it another try. That looks better. Okay, and so what we get here is a description of this network that we just set up. And if we now look at the trainable parameters, we'll now not print the values of these parameters themselves, but just the keys. And we see for each layer, so for the linear layers, we have weights. Okay, makes sense. But then for the this is, ignore this residual block. That's just my for loop that I set up a bit weird. But if you look, for example, here at this live layer, we have as trainable parameters tau mem, tau syn, bias, and threshold, just like we had it before with the 1 neuron example. And to be honest, this is way too much for now. We don't want to train all these things. So let's try defining our network again, but this time without these parameters being trainable. So how do we do that? We just import another class here from Rockpool that's called constant to declarate that these parameters are going to be constants and hence not trainable. So we just choose 50 milliseconds for the tau mem, 20 milliseconds for the synaptic time constant. Bias, we leave it just as 0. We don't need that for now. Threshold can be just 1. And well, okay, here there's also the dt specified. As if you remember all these simulation parameters and any parameter that is not trainable, they're kind of treated the same way. Okay, let's redefine our network. What do we need to do? We just do the same thing as before. We copy that here. I will write that again. And now, if you look at these parameters, they all refer to the LIF neuron, and we can just provide them as function arguments to the LIF constructors. So here we do neuron parameters. Same thing for the other LIF layers. And now we're basically telling Rockpool we don't want to train these parameters that we specified here, and we're telling it what value they should actually have. Now, if we don't do that, they are just initialized with some default values. Okay. If we now look again at what is trainable and what not, we see here, for example, for this lift torch, nothing, because all the parameters that were in there, we specified them to be constant. And if we now again look at the simulation parameters, we see that all these parameters that we previously had in the trainable parameters, they got moved here to the non-trainable ones. Okay, is so far everything okay? Am I moving forward too fast, too slow? Okay.
You have 15 minutes left.
That's perfect. Thank you.
I have one question.
Yeah.
So in the transformation, so you specified that you transform the lenses to frames.
Yeah.
Is that something for efficiency, or is that something that's required for Xylo to?
It's because usually you operate with time steps in these, because it's a simulation, right? And we don't have an event-based simulator, and hence, yes, it's required in this case.
That's also for on the hardware.
Good question.
There is a event-driven interface, so you can have an event-driven some sort of like a external output that brings drivers. But the simulation, if you're externally sending events, the simulation is blocked. So you can simply just provide them as class.
All right. The training loop itself this is really just as in PyTorch. You're basically training PyTorch modules here in a way, or at least modules that behave the same way. So I will glance over this very quickly. It's also very similar to what Jason did yesterday in his tutorial. So we define an optimizer that is directly imported from Torch. We define a loss function, in our case, a cross entropy loss. And then we define our training loop, which just iterates over the different batches in our data and gets an output from the network. The prediction from this output is just by summing across the output across the time dimension of the output. So basically collapse that. Then we count how many spikes has each channel produced, and we feed that into our loss function. And everything else is really just pure PyTorch. I won't go into that in more details. I actually also, with time in mind, won't train this now live because it will just take a while. Instead, I've trained the network beforehand and I'm just loading it from disk. We can do that. If you remember, net is the network that we specified before. We can load the parameters that we trained from a JSON file. So now let's run some data through the network. So I'm loading the data here. And then as before with the live neuron, I just pass the data in. Let's net.events. And let's see what the model did for this sample. So again, we have a raster plot. We have 8 channels for the 8 different classes, and the target class is indicated by this orange triangle here. And we see that this is actually where the model spiked most over time. And so, yeah, at least for this sample, the model seems to work. Okay, the Xylo architecture actually went into that. Okay, so now let's actually deploy the model onto this guy. So for that, we need to, first of all, connect it, of course. It's standard USB-C cable. And now, here. That's okay, thank you. Okay, so for that, we import a model that corresponds to this specific dev kit, again from Rockpool. And then later on, we will need a method that quantizes our parameters, because if you remember, the parameters are fixed precision. So now, in order to get from this trained model to a model that actually runs on hardware, we go through the following steps. We extract the graph from the network. That's this line here. We convert this graph into specifications for the hardware. And now in order to quantize our parameters, we apply this channel quantize operation on the specification. This spec here, this object, not to be confused with the chip spec, it's really just a dict. So all I'm doing here is just operating on a dictionary. So we basically update the values, the weight values here to be quantized. From that, I can get a configuration that will be loaded onto the chip. And from there, I can then load the actual configuration on the chip. And the way it works in Rockpool, we then get another module. So again, it behaves like all the other modules, the network and the live neuron that we looked at before. But instead of running somewhere here on the CPU or GPU with a torch as a backend, it will run directly on Xylo. For now, as a first step, because if you code along, you probably don't have a Xylo with you that you have connected. If that's the case, you can just here, instead of what I will show you later, you just set Xylo sim, which is a completely precise simulator of what's going on in the chip. Okay, so even if you don't have a dev kit at hand, you can at least experiment with it and see what does your model do, or what would it do if you deployed it on real hardware. Okay, so let's do that. That worked. And so now let's do the same thing as before. Let's run data through our model, but instead of the model from before, we will run it through the actual precise simulator that is not torch-based. Let's plot the output again. And that looks pretty similar to what we saw before. Again, the target class is the one that spiked most. So far, all good. Quantization didn't seem to have done much harm. That's good. And so now we can also, from the simulation, get the membrane potential for individual neurons. In this case, this would be the output neurons. It looks like that. But what everybody's probably waiting for, we can deploy that actually on chip. For that, we need to tell Rockpool to find the chip first of all. So it will check what is connected to the PC, is anything useful among that. And then when it finds the chip, we can select it. I know that there's only one connected, so I will just select the first one of those that it finds. And then, if you remember before, I wrote here Xylo sim as in simulation. Now I will replace sim with SamNA. SamNA is basically our intermediate layer, which we use to communicate with all our chips. And so let's do that. It actually found the chip and it now deployed the model. So now we do the same thing again. We run data through our model, but this time it's here, it's really on the chip. So now the input is going through USB on the chip, runs on the chip, and will read out the spikes from the chip.
While preparing the stuff, that maybe Markov chain Monte Carlo sampling might be interesting for people here. Markov chain Monte Carlo sampling is a technique that is being used in many different fields. So it's the connection to here is actually rather, I mean, you will see throughout the talk, it's kind of coincidental, I think, but it's nevertheless, I think, an interesting topic because it connects to many of the stuff we talked about. And so the reason I wanted to maybe talk about it a little bit is because of all of the different topics that we are talking about here in the workshop. So the recurrent resonance, constraint satisfaction problems, Ising models, simulated annealing, opfield networks, and so on. They are all connected, right? So at the risk of turning a bit like conspiratorial, there is something that all of these methods have in common, and that is that they're always talking about some system where the energy of the system can be like the Hamiltonian of the system is the defining feature, and we are minimizing that Hamiltonian over time. And this Hamiltonian in all of these cases can typically be written in this form here, which is also very reminiscent of the Q-port problem stuff we talked about. And one more thing that I found quite interesting is that in all of these cases, basically, if you want to simulate the systems, you can go back to the Metropolis-Hastings algorithm, which is kind of like a common core of all of these methods. So that's why I wanted to get into it a little bit and talk about like this Markov chain Monte Carlo sampling, but hopefully the connections will become clear. And just to give a little bit of background, like how I got to talk about MCMC sampling at all, the problem I was working on that had to do with MCMC sampling is actually completely disconnected from neuromorphic computing. That's it goes back quite some time when I was in university. And we had a project about predicting the leaf area index of winter wheat. So it's really like you have fields, you have wheat growing on the field, and there's a very laborious process where people go through the fields with a probe, and they measure how much sunlight hits the ground. And that basically tells you how good the canopy, like how much the leaves cover the ground area. And it tells you something about whether the plants are growing close to each other, whether they are ripe, whether they're growing well, and so on. And so this is a measure that farmers, for example, would be interested in, but it's a very annoying process to measure that. And so the idea was always like, couldn't you just put it on a, sorry?
Someone had a question in the chat maybe? Or?
Yeah, I cannot really see the chat, that's the problem. So maybe you can put up the chat on the side here.
Can I put?
No, you can click here, or you can just maximize the window here.
That's about it.
But we are in the same Zoom link all the time, so it's maybe from before. But yeah, anyway, so the idea then is, of course, instead of doing this manual process here, you would like to fly the drone over the field, do hyperspectral imaging, then you get spectrograms, and from these spectrograms, you would like to infer back these parameters that you can measure on the ground. And this is a very classical regression problem. So we want to predict the sleep area index of these crops from these hyperspectral measurements. And what made it complicated in our case was these measurements all came from different fields, like literally fields, different places, right, different soil, and so on. And also the plants might be different, like the ground might be fertile to different degrees and so on. Long story short, the data set is really segmented into different sub-data sets. And these data sets all have slightly different parameters that you would need to learn if you want to train a model on them. But the parameters are not completely arbitrary. They are all linked somehow. And in probability theory, you can build very nice hierarchical models where you say parameters of one data set are related to parameters of a different data set. And I don't want to go through this model in detail because it's just as a motivation, but you can imagine that if you write down these models, it quickly becomes complicated. So you're saying that, for example, some parameters on one field can deviate from a baseline parameter that is shared among all of the fields, but you also don't know the baseline parameter. So you're trying to learn all of these levels of hierarchy at the same time. And
what you do in probabilistic modeling is you write all of this down as probability distributions over parameters, and then you build up a model really like Lego pieces. You build up a hierarchy, and that describes then the whole system. But what we are interested in is now making statements about the system, and so we need to evaluate these probability distributions of this entire system, which we build up from all of these small blocks. And the problem is that these probability distributions, they can get really complicated. They are weird distributions that we cannot write down in closed form in a nice way. We can only give formulas to tell you how to compute this, maybe the PDF of this probability distribution, but we cannot do much with it directly. And so what you typically do is you write it down in some form like this, and then you put it into some solver. So in Python, for example, there's PyMC. There's also Stan, which is a solver from R. And you don't worry about it anymore. You don't think about what happens in the background. Now, the idea for this talk here was to look a little bit at how do these solvers actually work in the background. So what do they actually do with these probability distributions to allow you to answer questions, like, for example, extract parameter estimates from them. And so that's why we are going to look at sampling. And I specifically want to talk about this Markov chain Monte Carlo sampling, but I'm not sure what everyone's background here is. So I thought it's probably a good idea to start a step before that and talk a little bit about working with probability distributions, like a little bit of a primer. If this is boring you, just let me know and we can skip through it a bit faster. And so with probability distributions, you're probably all familiar. So you have probability densities. That's the basic building block. I will not get into probability distributions that don't have a density or weird shit like this. So it's true. You have probability density as the basic building block. And then you ask questions about this probability distribution. And these you typically write down as a function. And these functions are then called statistics. And the simple statistics everyone knows is the expected value of X, for example. So this is the simple function that if you evaluate this statistic, this identity function, evaluating in this case means you compute the expected value. That is just the integral that gives you the mean of the probability distribution. If you take as a statistic the function x squared and you calculate the expected value of that, you get the variance and so on, right? So these are the basic statistics that you have. And in general, statistics are more or less so expected values of some function of random variables. This is the only thing that you can really use in probability theory normally. So if you talk to really like Bayesian probability theory purists, they don't like stuff like maximum likelihood or something like this. They would say this is outside of the core framework of probability theory in a sense. So this is you're putting calculus in there and do weird stuff with densities. The main thing really is computing expected values. That's what people care about normally. And now the question is, if you want to calculate these expected values, you need to compute some integrals. And that is where it gets interesting. So how do you actually compute these integrals? And there are basically two different ways how you can approach this. You can go more or less the traditional route of calculus and do a Riemann integral. And that means you chop up the x-axis into bins of size delta x in this case, and then you evaluate the probability at all of these sampling points as I had here. And these sampling points are evenly spaced. You do the same thing for the statistic here that you're interested in, and then you just sum them up. And what you get here is that the area, you approximate the area of this real value thing here by just summing up these little rectangles where you know the width of the rectangle and you know the height of the rectangle, because the height is just the product of these two, of the probability and of the statistic that you want to evaluate.
So,
yeah.
What is GI? Is that the range statistic?
Which one? The
GX.
G of x, the function, that is the statistic, whatever statistic you want to evaluate. So for the mean, it would be x. For the variance, it would be x squared. For So this could be also something very complicated in principle. But yeah, so if you want to calculate this integral, Riemann integral, you just numerically, this is an approximation that you can do. The alternative to that, and this is what we are now looking at, is sampling. Instead of cutting up the x-axis evenly, you can also just draw samples where the density of the samples is equal to the density of the probability density that you want to work with. And so here you don't put any values into the probability density. You don't evaluate the density directly. You just take samples where the density of the samples itself is proportional to the density that you drew them from. So the green bars here should be closer together where the probability distribution is higher, right? And now you plug these same samples into the statistic you want to look at, and now you can also estimate the integral by just doing basically averaging over these sampled statistics. These two look very similar to each other. The interesting thing is in this expression down here, you no longer have this phi term, you don't need it, because the existence of the sample already includes the probability of that variable. Now, if we go to higher dimensions, and so yeah, what I want to show here is like in the end, to calculate these expected values, actually you only need to have good samples from the probability distribution that you're interested in. And now, if you do this in high dimension, it's the exact same story. So you discretize the higher dimensional space now. You evaluate the statistic you're interested in, also like in a rasterized way, and then you integrate again. And now you have an integral here or a sum that goes over all of the dimensions. So you can imagine that if you discretize with a certain resolution, it grows with the dimensionality, like to the power, right? So it exponentially grows with the number of dimensions you have. And the problems that we're often interested in are actually like 100-dimensional or something like this. And so you don't want to discretize a 100-dimensional space with a high resolution, because it means you need to do an enormous amount of calculations. On the sampling side, it's a bit nicer, because you just, if you have samples from this distribution, you do the exact same thing as before. You evaluate the statistic on the samples, and then you just average. And this does not grow with the dimensionality. So you might need more samples to cover a high-dimensional probability distribution well, like to get into every Lac and Kearney of this distribution. But you don't have the same problem as you have with the traditional approach, where you actually need to increase exponentially with the number of dimensions. Because if you draw 100 samples here in this two-dimensional space, and then you only care about what happens along one of the axes, you have 100 samples along the x-axis that are good, you have 100 samples along the y-axis that are good. In every dimension, you have a good number of samples, so you're fine, right? The problem is how do you get these samples?
You can look at it independently.
Yes. Yes, and that's, I think, what I already what I have on this slide here. So if you think of this like two-dimensional distribution here, there's two different views you can look at it. So you have two variables, x and y, and you can either factorize it out in this way. You can say the joint distribution here is the product of the marginal distribution along the x-axis times this conditional distribution along the y-axis. But you could equally well do it the other way around, right? You can also factorize it in terms of the marginal distribution of y and then the conditional along x, right? And so if you take these two different ways of factorizing it, you can put them together. This gives you base formula. And this is something that, just as an aside, it's important to keep in mind. This is something that people in probabilistic programming often care about. This tells you the probability of seeing x given y, when all that you know is the probability of seeing y given x times the probability of x. Now, if I plug in some interpretation here, so x could be your parameters, and then p of x is a prior assumption that you make about your parameters. For example, my parameters should be close to 0. And then y could be the data that you have observed. And so you could think, if I have a generative model and I put in some parameters x, what is the data y that I will observe? That's the forward pass of the model. And you're interested in the inverse pass. You're interested in knowing what should my parameters be if I observe the data y, right? And this is what in probability theory, what people mean when they say inference. So it's solving this inverse problem. And what's, and just a bit of terminology. So this term here is then called the posterior. This term here is called the prior. and this term here is the likelihood. So prior is the prior belief about the parameters in this case. And this time down here, this normalizing factor is called the partition function. And this is something that, as you can already imagine, this is a very annoying quantity that you don't really want to have to calculate all the time. We will later see that we can do without this. Just know that there is this factor in the denominator here that we are trying to not care about too much. And yeah.
What is the factor actually calculating? Is it calculating the average over all the?
Yeah, so this is basically just from the definition of a conditional distribution, I didn't want to go into that, but you would say the conditional is the joint distribution divided by the marginal distribution of the variables that you want to condition over, right? And this time here, this will tell you the prior probability of your observations of the data, but most of the time you don't know what the distribution of your data is going to be. That's something that you don't have control over. You can calculate it by saying, okay, what are all of the different parameters that I could put into my generative model, and what data would it generate? And then you integrate over all of this, and then you get an answer for what distribution of data to expect. But this is not something that you actually want to calculate if you can avoid it. Yeah, and what I wanted to show in this picture here is to the point I made before with the dimensionality. If you manage to draw samples from this higher dimensional distribution, then you automatically have samples for all of the marginal distributions. Because if these samples here really reflect the joint probability distribution, you can just ignore the other coordinates. Like you have a sample xy, you just ignore the y coordinate, then the x's are good samples from the x distribution, the y's are good samples from the y distribution. So if you have a joint distribution and you have samples, you can also answer questions about marginal distributions and expected and conditional distributions. And it means samples are really all that you need. If you can generate good samples, you can do all of the statistics that you're interested in. And now, how do you actually do this? Like I just showed you take samples, and it looks easy, but it's actually not so straightforward. So let's assume we want to generate these samples, these white dots that I showed before, from some complicated target distribution P of x hat. And the only things that we know how to do is, given a sample, we can plug it into the density function and we can compute the value. We can see this has probability density 0.3 or something. But we do not know how to create a sample that comes from this probability distribution. That's what we're trying to figure out now. We do know how to draw samples from very specific simple distributions. So we know how to generate uniform variables. We know how to generate Gaussian variables. That's all that we want to do. With that, if this is all that if these are the requirements, what we can do, and that's the thing idea, why not draw samples somehow here? Okay, just a rendering area. Anyway, so we draw. So we pick a simple distribution, some multivariate Gaussian, for example, where we know how to generate samples. Then we introduce a new variable called A here, and this variable is basically a coin flip. It says, do we accept the sample or not? And it is a coin flip, but the probability of the coin flip it's not a fair coin flip. The probability of accepting it somehow depends on the sample. So we look at the sample, we decide what coin to flip, we flip it, and if we accept it, then we say this was a good sample, otherwise we reject it. And now if we do that, we get a joint distribution over samples and whether or not we accepted these samples. And if we now only take those samples that we accept, we hope that these samples now magically, they should come from the target distribution that we're interested in. And the question is, how do we need to decide on the probability of the coin flip to make sure that this happens, right? This is the problem that we need to solve. Like how to set this acceptance probability. If we manage to do that, the process of generating samples becomes very simple. We draw a sample, we decide whether we accept it or not, and if we accept it, it's a sample, otherwise we try again. So how can we make sure that this thing here holds? Well, we want to make sure, this data is very slow on the Zoom. So we want to make sure that the probability distribution of the samples which we accepted, this distribution should be equal to the distribution we want to sample from. And we know from this base formula that it's proportional to the probability of accepting a sample X times the probability of proposing a sample X. And now, what should we plug in here to get out on the right-hand side this P of X hat? Right, that's the trick. What can we plug in here so that this whole term here cancels out this P of X and instead gives us this target distribution P of X hat? That is basically, we need to say this acceptance probability should be somehow proportional to this ratio here. And the ratio says how much likely is the sample, how high would the probability of this sample be in our target distribution, divided by how likely is it to draw the sample from our simpler sampling distribution.
Sorry, can you repeat that?
Yes, so we want to set this acceptance probability here so that the probability distribution of the accepted samples becomes equal to the target distribution. The target distribution was this P of X hat here. What we have is the P of X. So we want to choose this to basically substitute the P of X here with P of X hat. And we can do that by, if you just plug in this ratio here, you will see that these X's cancel out and you're left with the target distribution, right? So the acceptance probability here has to be somewhat proportional to the ratio of these two. This is the target distribution, this is the distribution that we sampled from, like the multivariate Gaussian or something like this. And so this is called rejection sampling, and I think it becomes clearer if I show a picture here. So we have the simple distribution that we know how to generate samples from, and we have this target distribution that we want samples from. And we can compute the ratio between the two. And now we do a two-step process. We draw samples from the simple distribution. For each of the samples, we flip a coin, and the probability of the coin is determined by this ratio. And so you see that we accept a lot more samples here and here, where the ratio of the probability that we want divided by the probability that we sample from is high. And if we do that, you only take the green samples, only the ones we accepted, you end up with samples that come from the target distribution.
But Johannes, you don't know the sample, so you don't know the target distribution, right? That's what you are trying to get to.
You know from the target distribution, you know the density function, and you can evaluate it. If I give you a sample, you can decide how probable is the sample.
So you use the density function. And
yes. Yes. So the density function, you can evaluate it, but you cannot. I cannot ask you, give me a sample from this distribution. You can give me a sample and I can tell you, this is a very unlikely sample or this is a very likely sample. Right?
You know, this will not work well if the sample distribution has very low density.
Yes.
Where you really care about having very high density.
Yes, exactly. That is the problem. So if on the slide before, basically I was saying the acceptance probability has to be somehow proportional to this ratio of probability distributions, but the acceptance probability has to be smaller than 1. So you need to rescale it so that you don't get probability of 5 or whatever of accepting, right? So you need to this ratio here, for example, if the probability in the sampling distribution in the denominator is very low, you divide by a very small number, so this gets very high. This ratio goes to infinity. And then you need to counteract that by making C smaller and smaller and smaller. And what that means is, and I try to show this in this picture, like for a one-dimensional case, you basically want the sampling distribution and you want to scale it so that the target distribution that you want to generate samples from fits under it somehow, right? But all of this space in between here corresponds to samples that you would draw and throw away. So basically, in order for this to be efficient, you need to find a sampling distribution that is very close to the target distribution. And normally you just don't have that because the target distribution here is a complicated thing. And finding a good sampling distribution to draw from is not possible in most cases. And so this is very inefficient, and it's particularly inefficient if you are in high dimensional spaces where this technique works.
So may I just build up on what Kurt asked? So it seems that for this to work, your given distribution and the target distribution should have some significant overlap, right?
Yes. Yeah.
Otherwise, I mean, the basic formulas are things right now.
Yeah, they need to, so they need to, or if they don't have an overlap, it just becomes, you need to draw many samples until you.
Inefficient.
Yes, it's extremely inefficient. And so of course, if you manage to if you hit the target distribution exactly, you just take the sampling, your target distribution is equal to the sampling distribution, this ratio will be 1, and you will accept every sample, like you will not waste anything. But in practice, you don't, right? And if you think in a high-dimensional case, where you have a distribution that has some peak somewhere and then is flat in many other spaces, you kind of need to scale this for the worst case, right? And so you have a lot of dead space in a sense, where you keep drawing samples from and just throw them away. And so this is really bad. If you do it in high dimensions, it's even worse. And that's why it's a nice idea, but in practice, it's just not very useful if you want to draw samples from a complicated distribution. And that's why we need to do this Markov chain Monte Carlo sampling, which builds on this idea, but it's a little bit more involved. So maybe if there are questions until here that we need to have answered now.
So I mean, this is something I haven't thought about it before. So maybe if I'm not the meaning of the question, that would be great. Feel free to correct. It seems that the Markov chain Monte Carlo you need and the release name for Anderson is probably less applicable. Is that a fair statement?
Not really. I mean, people who do Bayesian probabilistic modeling rely entirely on Markov chain Monte Carlo sampling. You need it when you want to make statements about expected values of the distribution. The distribution is difficult. Maybe you don't have it in closed form, and you need to generate samples so that you can estimate these values. But to generate these samples, you need a method, a reliable method that just works. It is kind of efficient, and the rejection sampling is kind of a naive thing you put in, but it doesn't work very well. And that's why, and so we will now see how you can make it better. So these are the same assumptions we had before. We will now add one additional assumption, and that is probability distributions that we care about are probably smooth in some sense. So if you found a sample that has high probability, there are probably interesting samples around that as well. The rejection sampling just draws a completely new sample at every time step from the whole probability, from the whole space. It draws new samples. But if you are close to a peak of a probability distribution, probably you should draw more samples nearby. And so the Markov chain Monte Carlo sampling takes this into account and basically drawing a new sample, but it uses the information from the previous sample. That's why it's a Markov chain. It's the new sample is drawn depending on the previous sample. And so the idea here is, instead of drawing a new sample again from the sample distribution, you only draw an update step. So you start with the previous sample and then you move away from the previous sample in some way. And then again, you check whether this movement made sense for the target distribution you're trying to approximate. And you again flip a coin to see whether this was good enough or not. Yeah, that's a very underlying idea here. And so to make it a bit more concrete, and this is the algorithm that people basically build most of this honest metropolis thesis algorithm, kind of works like this. You draw a sample X, and then you have a simple distribution again, like a Gaussian, for example, and then from this Gaussian distribution, you draw how much you move away from this initial X. For example, we move to a new candidate sample here. We check, do we accept it or not? In this case, we didn't accept it. We try again, we draw a new sample, and we decide whether we should accept it or not. And the samples that we accepted, they come from some distribution. And we again want, just in the case before, we want to make sure that this distribution is equal to the distribution that the first sample came from, because both of these should be equal to the, I think it's, yeah, this is somewhat rendering in a weird way. There's, actually, I'm not sure if you can see it. It's an asterisk. It doesn't show very well. Anyway, so we want our samples to come from this distribution here. I think it was X hat before. I'm sorry about that. But so we want the sample to come from this, yeah? And so that means the previous sample that we drew should have come from that distribution already. And the new sample we drew should again come from this distribution. And so, yeah, so this is the new distribution, this is the distribution of the previous sample, and this is the target distribution that we want to generate samples from. So how can we make sure that the updates that we do don't destroy, so that if we had a sample that comes from the good distribution and now we move somewhere else, how do we make sure that this new sample still comes from the correct distribution? That it doesn't destroy the distribution that we're sampling from. And there are different ways how we can do this. The smart thing that people did for this Metropolis Hastings algorithm is the idea of detailed balance. So the idea here is that the probability of drawing a sample S and then going from S to X should be equal to the probability of drawing a sample X and then going from X to S. So it's basically the two paths. If I go from here to there, it should be equally likely as going the other way around. So it's always, in a sense, like going from one sample to the next doesn't make it impossible for you to just go back in the next time step again, right? And so if you, this is not the only way to do it, but if you do this, you can show that drawing new samples you will stay in this distribution and you will just keep generating new samples from that distribution. And it's, I was thinking if I can show this without putting a bunch of formulas here. I didn't find a way, so I'm sorry, there are no formulas on this slide, but it is how it is. So,
but this has proofs of ergodicity.
Sorry?
This has proofs ergodicity.
Ergodicity, yeah, I mean, so there
time doesn't change, otherwise it should be something.
Yes, I mean also the concept of the concept of detailed balance. There's a lot of interesting interpretations you can put on it in physics. I'm here just really looking at the just from a probability perspective first, like the connection to energy and stuff like this. We'll do a little bit later, but yeah. So, yeah.
So if you're always trying to make the growth pathway that you don't want breakout room, then it's fine. There nobody's in. Yeah, just these.
So yes.
Because it's not comparing it to the target.
This is a condition that has to be satisfied to make sure that the distribution stays invariant. So if I have a couple of samples and then I go from these samples to new samples, the two distributions should be the same. This does not say yet that is the correct distribution. This just says the distribution doesn't change over time. It's a stable distribution. And that's a condition. It has to, like, if we don't have a stable distribution, if you keep generating samples, you will not from changing.
You are in our breakout room, but you can.
But it does not. This does not yet guarantee that the samples you get come from the right distribution, right? But we can work our way down from here. Yeah, we can see. So here, this term here that I put in here, that would mean we had a sample S in the previous step, and now the next sample is X. This step consists of two textual steps if you look at it in detail. Yeah, and that's why I split it up here. Going from X and taking S as the next sample means we went from X and we proposed S as the new sample, and then we accepted it, right? Because we introduced this coin flip. So we have to make a proposition, and then we also need to accept that proposition. And this thing here we have not yet defined what it should look like. Yeah, and that's what we need to choose now. How do we choose the coin flip? The same as in the case before for rejection sampling. How do we choose the coin flip here? And if we put in this condition here and just plug in this equation, rephrase it a bit, you get this expression here. And what the Metropolis Hastings algorithm now defines is it sets this acceptance probability as this formula here. And that might sound arbitrary, right? It looks a bit arbitrary. If you want to go through it, you can very easily check that if you plug in this form on the right-hand side into this equation here, it will simplify. So you have you just pattern matching, yeah? No, because it's a bit too difficult to try to understand it like in terms of probability theory, but just pattern matching. This term here shows up on the top of this fraction here. And then on the bottom of the fraction, we have the same term with the x and s just switched. Yeah, if we look inside this equation here, we see that if we switch the s's and the x's, it's just the inverse of this fraction here. We just flip the fraction around. It's the same, right? Switching the s's and the x's just means you turn this fraction on the right-hand side around. And if you plug this into the ratio, you see that we have a function of this form. We have a minimum of 1 comma v divided by minimum of 1 comma v inverse, where v is this whole colored term there on the right-hand side. And this sort of thing, these two minima here, it just simplifies to putting a v there. So if you want to go through the derivation, you can sit down, look at it a little bit, think about it. The upshot of this is, if you want to satisfy this detailed balance condition, one way you can do that is by choosing the acceptance probability how it is shown here. And this is a very popular choice. And this form here is called Metropolis Hastings. There's a simpler version of this tool where you only have the purple term here, and that's called the Metropolis algorithm. That was the original one. People made a variation of it. That's the Metropolis Hastings. This will show up in a lot of different contexts where people do Markov chain Monte Carlo sampling or other related things that I want to get into now. But maybe even if this, like the entire math is not clear, I hope that the rough intuition is somehow clear, right?
Can you spell again the 1? Because if it's 1,
yeah.
Oh, the 1 is because we probably can't exceed.
Yeah, but in that case, it's not a measure.
It is actually not an approximation. I mean, the motivation behind it is sort of that if this fraction became higher than 1, you would have a probability higher than 1. But it's actually not an approximation because so it's harder to motivate why this choice is good. It's easier to check that this choice is correct. So if you say the acceptance probability is this function here, and you just plug it in here, you will see that the detailed balance condition is satisfied. So if we just do this like it's a bit unsatisfying for a second in high school when people just say, take this ansatz and then you can verify that it works, right?
Right?
That's exactly.
The detailed balance is just like the TV. So if you have more particles to this side, you pick the particle to move to this side.
Yes, exactly. So the particles, you have a lot of particles on one side because they are attracted to that side, for example, then they are unlikely to move to the other side, but you have a lot of them. On the other side, you have very few, but they are attracted to the other side, so the probability of moving is very high. So if you multiply the two together, they should be equal. That's basically this detailed balance. And this is just one way how you can satisfy it. And I put this derivation here that you can just see formally it does work out.
Is it the best way of doing it? I guess so, because otherwise someone will have come up with it.
I actually don't.
This is why it's called the Markov process again. This detailed balance.
Yes. I mean, the detailed balance is a property that Markov processes would have. Yes, yeah, or maybe not. So, I mean,
detailed balance does not imply Markov. Because detailed balance is used in chemistry.
Yes, it does not.
It's just
Particles are conserved.
Sorry?
Conservation.
That's right. So if locally the fluxes are conserved, then there's symmetry.
Right.
So
and you can see if you sum the left side with respect to x, you will see the x marginalizes out. Right. So then you just left with the probability of x. So it becomes the forward, backward, and forward equation. So if you sum both sides with respect to x. So that shows the conservation of probability too.
Yeah.
So now how do you analyze this?
Yeah, so maybe I will get to the I think a slightly nicer part of this now. But this was the brutal math thing. But I actually, for me, I think it was really important to have a feeling, kind of to understand, because this is weird when you just read the formula, it comes out of nowhere. Like, why do you do this acceptance probability like this? But it does make sense. You can understand why it works. And then you can use it to do cool things. And now I have a couple of videos to just show like what you can do with it. So here again, we have the target distribution that we were interested in. And the sampling distribution, as in the picture I showed before, it's just you take the sample that you started from, you do a step somewhere nearby with a Gaussian, and then the acceptance probability is just what we had on the slide before. Only in this case, because the steps that we do are Gaussian, it's like it's symmetric, right? Going from one starting point to a different point is the same probability as going in the opposite direction. So these terms in this case just cancel out, which makes it a bit simpler. But it's the same basic thing that we plugged in. But you can now see here
for non-Gaussian sample.
This is, I mean, for symmetric distributions, these terms would cancel out. Yeah.
Sorry, what made them cancel out that they are both same?
The green terms here would cancel out because we always take a sample, and from that sample we do a step that's just drawn from a Gaussian distribution, and the probability of going from this point to this one using a Gaussian centered around this point is the same as going from this point back to that one with a Gaussian centered around the other point. Like it's because the steps are all Gaussian.
But it did not cancel in the previous one.
The previous is the general
because it was more general.
Yes.
But this Gaussian automatically you're saying cancel.
Yeah. So in this formulation, so the video, by the way, like it starts very slow and then it speeds up a bit. So that in the beginning you can, I need to actually go back to the previous slide to restart the video, so you can watch the video in the meantime. So yeah, in this case, the green terms cancel out because the updates that are done are just drawn for the Gaussian distribution, which is symmetric. Yeah. And so, as you can see, it goes from sample to sample, evaluates it. The ones that I kept, you should see the line going green. Some of them are rejected, the line goes red. And in the beginning, it takes a while because we started in a random place, which maybe has a very low probability. And so this takes some time until it settles and the stationary distribution of this process approaches the correct distribution. And once you hit that, it basically keeps generating samples that are good. And if you let it run, you will end up with a distribution of samples that is very good, like it matches the original distribution. And so this is something that already, in theory, we could use. This is what people already do. There's just one small thing that we would like to make better, that is these steps are very small. And so two subsequent samples are very correlated. And what you ideally want is one uncorrelated samples. And so we would like to have some way of sticking with this basic idea, but instead of making very tiny steps from one sample to the next, where then all of the samples nearby are closely correlated, we would like to make bigger steps. And this is where I think a very beautiful idea comes in, and that is the Hamiltonian Monte Carlo sampling idea. And for that, I think it makes sense to rewrite this, which was so far it was all written in terms of probabilities, to rewrite it in terms of energy. So far we said we have some probability distribution that is Gaussian and it has some exponential form. And then you can just say the argument of this exponential, that's the energy. And you just rephrase it. Instead of saying you talk about probabilities, you now talk about the energy level of a sample X. And these fractions here, because if you plug in these exponentials, they just turn into differences of energy. So now we are saying basically we want to accept a sample based on how much this sample, the energy of the sample changed relative to the energy of the previous sample. And so samples where the energy goes down are good because this, the system should be in a low energy state. So we should accept them. Samples that increase the energy are bad, but we sometimes want to take them because we want to still explore the whole probability distribution in a sense. So that's one way you can interpret it. So if the energy goes up, then we are at the point we exceed 1 and we are basically clipping at a probability 1. So samples that decrease energy are always accepted. Samples that increase energy are sometimes accepted, depending on how much they change this energy. It's just a reformulation. There's nothing new here. It's just rewritten in terms of exponentials.
One could argue the minute you put the Hamiltonian in the canonical ensemble, it is Gaussian in terms of quadratic variables, right? If you look at the Maxwell-Boltzmann distribution, it would be a p squared So,
I'm not sure. I'm not sure.
so I'm saying that it is, you can transform that into a Gaussian distribution as well.
If this energy is some quadratic function.
That's right.
Yes. Yeah. Exactly. Yes. Yes. And so in the case of symmetric distribution, again, like the screen terms cancel out, and it gets even simpler. And this is the most simple case, I guess. And now for the Hamiltonian Monte Carlo sampling, it's the same story as before, but now, as I said, we want samples that are not so close to each other. And the trick to do here is we basically do the same process as before, but instead of drawing a sample from a Gaussian centered around the previous sample, we say the sample is now a particle, and the particle now has momentum. And we now simulate the trajectory of this particle, and we take the probability distribution that we sample from really like a gradient field. And now we are simulating this particle as it moves around in this gradient field. And the logic behind it is, if we include this momentum term in it, we have a Hamiltonian where the kinetic energy, if you want to translate it into a physics language, right, the kinetic energy would be whether the position of the sample is at a point of high or low probability. And then there is the kinetic energy that comes from this momentum term, which we just invented. And as long as we have a good simulation of this particle, the Hamiltonian does not change in that case, right? You move energy from the potential to the kinetic energy or vice versa, but the energy level is the same. And so, because this is maybe a little bit too much to go into detail, I think it's again maybe easier to have a picture to look at. I put the equations here, so the idea is really very like it is not too difficult to understand if you want to. So you now have the position of the sample, that's the thing that we care about, but we also have this made up momentum term, in this case m. And we just draw the momentum now from this normal distribution. And then we just, we say the energy of the system is now the potential energy here, which is basically just the log of the probability distribution, plus the kinetic energy, which is just depending on this momentum term. And then we really just simulate a particle moving in space, just an ODE. And the acceptance probability is as on the slide before. It's just for each sample, we can evaluate the energy that it has, and we can decide whether the energy change, the Hamiltonian, like this total energy change. If it lowers the energy, we will always accept it. If it increases the energy, we will sometimes accept it. And in the video, hopefully you can then, oops, in the video you can
actually accept well, because the particle is in motion, right? Accept the momentum, accept the.
So you accept the sample, but the momentum term you're not interested in. So you then, after you accepted the sample, you basically take the x position of the sample that you got. This is your new sample. The momentum you throw away, you randomly generate a new momentum term for the next sample. And the idea there is that by choosing a random momentum term, you are taking, after each sample, you take a new randomized momentum term. And the idea is that you draw from a different energy level of the system by starting at some position, but then with a random momentum. If it has high momentum, it has high energy. If it's the momentum term is small, you have the low momentum.
Sorry, Johannes. So it's not random momentum, right? You're taking the gradient of the logarithm of the probability. So
the initial state. So
I see. You don't use it then. I mean
no, afterwards you take one sample, you just take the position, you draw a momentum term from a Gaussian, for example. Then you let this thing, you have the initial condition of position of momentum, you put this into an ODE solver, just let it run for some period of time. And then at the end, you look only at the position, you look at the position and momentum term that you ended up with, then calculate the energy, the Hamiltonian thing.
And then you calculate the momentum again.
Then you decide whether to accept or reject it. If you accepted it, you use the position that you landed as a new starting point, but you now start with a randomized momentum.
And if not, you go back to the previous one.
And if you rejected it, actually in this case you actually repeat the previous sample. So,
yeah.
But yeah,
with different momentum.
with
Of course, a bit more.
yes, with a different momentum. Otherwise, it would get the same thing. And so, as you see this here, like actually, the simulation is now not just doing a Gaussian update step, but it's actually really doing trajectories in the space. And in the beginning, it's rejecting a lot of them, but again, it takes some time for this distribution to settle. And then once the stationary distribution of this matches the target distribution, it keeps generating very good samples. And as you can see that the distances that you can cover are much larger. Before you can only do small Gaussian steps around the starting position. So this will also speed up as we go along. The benefit now is, it looks very similar, but the benefit now is that nearby samples are less correlated than they were before. And that means if you want to use these samples in some way where the order matters, otherwise you always have the problem that you can only take every 100 sample or so, because you're not sure if the samples between are just too correlated to the samples already solved.
Just to summarize, so the insight here is that by energy is square, you always bring the same positive, relatively positive. By doing momentum, you can actually have MV, which is really, you can pick a direction which is orthogonal or different than where you.
But the momentum, even in the Gaussian case, you could go in any direction. The thing that this has enabled, based on my understanding, is you can take longer time steps, which would not be because of
yeah. So here basically
that's only the other one where Gaussian steps small.
This slide doesn't show that you simulate over time.
Right.
Yeah, so I try to indicate that by showing, like, seeing the particle move on this trajectory. So yeah.
Otherwise, you go, why would equal it?
Right.
Yes. Yeah, you're right. Yes. Absolutely. So it's really you really simulate the path, and the idea is that you basically stay on an isopotential line somehow. Like you start somewhere, and then you go as far as you can in this probability distribution space, whatever you want to call it, without changing the energy level. And if you sample from the different energy levels, then you get good samples from this distribution, and you ensure that you sample from different energy levels by randomizing the momentum. So that's
because you're absorbing energy in this, right?
Yes, you're conserving energy, and that's also why you need to then use some solvers that actually conserve energy. So it's like leapfrog integrated stuff like this. So you're really solving, like you're simulating particles, which is I think is quite cool.
Do you always simulate them for the same amount of time, or does it make sense to randomize that amount of time as well?
Yeah, so I think there are some very sophisticated things that you can do, how long you simulate it. So one of them that people actually use is then called no U-turn sampling. So you're trying to take it to, because it could be if you keep just going that you just end up at the same point as in the beginning. You don't want that. Right. So you then have some cut-off criterion where you say, okay, now I've gone far enough, now I start going back again, maybe I should stop here. And so there's a lot of tricks that people do.
Yeah, you can have dissipation here too, because you don't need to conserve the image. So then you will not end up with the same cycles. You will not see always.
Yes, but actually, maybe I should wrap up that. So I added. I think this is the core ideas that I found quite interesting, and I just wanted to tease. I really just want to tease because I found this connection interesting. So if you go to something completely different, Ising models, which Berthold will talk about, for example, you can think about them in a very similar way. You can say from one sample to the next, you do a change. In this case, the change is you flip some spin. And the energy of the system you can write down. It's this equation that it shows up all the time in all of our talks somehow, right? The energy is somehow the coupling between neighboring nodes. And you can run the Metropolis algorithm where you decide whether you randomly choose a position to flip. And then you use this same Metropolis algorithm to decide whether you accept this flip or not. And if you let that run, you can see, so in this case, it accepted a flip, up there it accepted another flip, here it accepted again, sometimes it will reject some of them, maybe it will back in. So in general, it also it should accept more than the
Johannes, what are those yellow and?
Yes, doesn't maybe I should say. So this is just anyway. Yes, I was thinking to just put an image here, but I found these pixels hard to look at. They look like QR codes, and it's very difficult to look at them. So it's the same thing, just as a control plot kind of. But if you keep this running, you will see that this is the standard thing that you always see with Ising models, that like you see this formation of like bigger patches, right? It's the system organizes itself, and this will also speed up in a second. What I found interesting, it's like this is a completely different type of problem, but you use the same idea as the Markov chain Monte Carlo sampling to accept or reject samples. And the intuition behind it is you're drawing samples from a probability distribution that is really complicated, and in this case, it's a probability distribution over states of this Ising model that are probable. We started in a state that is highly improbable. It's completely random. That is a very unlikely state. So if you let it run, you end up getting states that are more likely. And this, for example, is a more likely state for this Ising model. So this is not an optimization algorithm. It's just a sampling algorithm, which you start with very improbable samples, and if you just let it go, you get more probable ones. And it's funny somehow that you can use this to minimize energy, even though this is not trying to minimize.
In a thermodynamic sense, right?
Yeah.
It's like temperature.
Yes, so if you need beta, then you can do neutral optimization.
Yes, and annealing is a nice keyword. I just wanted to put so because I just wanted to try this yesterday, and it actually works too. You can do the same game again for traveling salesman. You can say, I have a sample which is a potential solution for traveling salesman. How do I go from one sample to the next? A simple heuristic could be, okay, I take some random subpulse of this and I either flip it around or I shift it to somewhere else in the sequence. So this is how you go from one sample to the next. And then how do you decide whether you accept or reject the sample? Well, it's again, you need to look at what's the energy of this solution. And the energy consists of, in this case, of three different terms. The first one is really how good of a solution do you have? And then these other two terms are constraint terms. They say basically every one of them says every node should be visited. The other one says every step of the sequence needs to be covered somehow. Like at every step of the sequence, you need to be at some node. And so you rephrase this problem. You just say this is the energy. And then you let this one run, and
the same energy that hospital use.
Yes, yeah, I think so. Yes, and so this is now a traveling salesman for the 47 US state capitals that are not in weird places. So I think like the mainland or everything. And so it's now just drawing samples. And again, it's not an optimization algorithm, right? It's not an algorithm that tries to find the optimal solution. It just tries to generate samples that are reasonable, in the sense that are likely for traveling salesmen. And we said sample like solutions where you go over long distances are unlikely.
Likely,
yeah.
So it means
better. One comment on this is there is an implicit optimization, right? Because you took from a canonical partition function, canonical distribution function, which is energy minimized with certain constraints. So in a way, it is minimizing the energy because your distribution from which you are taking is derived from statistical
or
as a minimal energy.
Maybe how I would phrase it is we just find here that the probability goes up as the energy goes down, and we want
so in a way it's implicitly an optimization.
Yeah, exactly. So now
so when you
I have to speak on behalf of the organizers.
There's another
group and they're about
so
the quantum group.
Yeah, we're passing on the Okay, then I will just cut off here, but ask me questions about this. I will also, like all of this stuff, it's basically built on the same very simple Python code, which I will put on the Colab as well. And
the prioritization will be the problem, right?
So on the Slack channel, I'm gonna put where in that is for people to play.
Yeah, we sent the link around for the folder. I will send something around when I have will clean this up a bit for the notebook, but then I will send it.
And I put a link on Slack already to a notebook that I made a few years ago on this stuff. It doesn't include the Amazon and pretty much everything else.
Okay, nice.
Maybe you should give us a tutorial. We convinced to show up from Australia.
Okay, so then I will connect for the video. So thanks for coming here. And as a more get all the information to make place for the other.
So yeah, I will give an introduction about the SpiNNaker software and like how to use it for coding networks and doing stuff in this workshop. So yeah, maybe let's start with a general overview of the SpiNNaker software stack. Maybe did anybody use SpiNNaker 2 before? Yeah, or SpiNNaker 1 actually. SpiNNaker 1. Okay. Yeah, so one part is doing spiking networks, right? So we want to use Spline to do that. And this is like the SpiNNaker 1 interface as well. But also we want to use, deep learning frameworks for inference in SpiNNaker. And this is like, one approach to do that is using the Apache DVM. But also we are interested in a generic implementation. So we're interested in giving users the ability to code whatever algorithms they want to do with SpiNNaker. So we had roughly one example. Genetic algorithms, for example. So this framework should allow users to have the flexibility to do anything on SpiNNaker. Now to do that, we are kind of reusing a lot of packages from SpiNNaker 1. So we need to adapt them for SpiNNaker 2. So there's one person in Manchester now responsible for that. So these packages are responsible for the interface between the host and the chip and communication and that low level stuff. So as I said, for the SNN part, we're interested in using the FINE interface. So for that, we reuse the SpiNNaker package. So we probably create like SpiNNaker 2 package for that. And availability for this part is probably like realistically next year. And also this is going to be for the 48 node boards, maybe a bit earlier for the single chip system. For the DNN processing, Matthias knows more about that.
Yeah, so for the DNN, so that would be in this case pure DNN. We are planning to use the Apache TVM framework. That's a framework where you can basically load in a neural network from PyTorch, TensorFlow, Onyx, whatever you can imagine. And it will compile this through some kind of intermediate representation into whatever hardware you want, basically. So by default, they support GPU and CPU code, so it can directly spew out C code for any model that you generate. But of course, just having C code is for the SpiNNaker 2 not really what we want. We want to support the accelerator for matrix multiplication, for convolution, stuff like that. So this is all still work in progress. So we will have to provide our own backend. And what we have is currently for a single core, the C code generation. We tried that out. We did it and used this model also in real time. That worked fine, but everything that is beyond single core and pure C code is still work in progress.
Depends on the exact neural models that you want to use, but if you're talking about this coupling, for example, with these oscillators, then you probably have to write some C code for this neural model. So
but only for the neural model, right? Yeah. Everything else, like running the neural model in a loop, doing the communication, all of that is taken care of, right? It's like SpiNNaker 1. If you want a specific neural model, it needs to be hardcoded in Z, but only the neural model. Okay.
And the third part is just running hybrid networks. It can be complete SNNs, it can be NNs as well. It's using this SpiNNaker 2, which is a lightweight Python interface for SNNs. And we go into details about the syntax and how to define networks. This is available now. This is the most mature software package to use SpiNNaker 2 state, I would say. So to quickly go over different repositories we have. So we have, SpiNNaker 2 is the most mature one that I just mentioned. There's another repository for the low-level DNN stuff. And then this is the S2 Sim2 Lab app. This is the low-level definitions of neuron models, dirty rules.
Basically also just the hardware drivers.
Yeah.
So that's the stuff you definitely need. Hopefully you don't have to touch it unless you want to do something very specific.
So, the last.
Sorry, go ahead. I mean, I had a question on this.
The last one, SNN torch to SpiNNaker paint. This is the stuff you did last year, right?
Yeah, this is work that started last year here, and then we are having discussions about extending that.
And this low-level software, do you use the ARM libraries for neural networks and all the DSP libraries? Is that
the DSP libraries doesn't make sense because it's only an M4F. It doesn't have DSP functionality, right?
Yeah, it has some kind of DSP
functionality. Very limited, yeah.
But we have this big inference application unit. So usually you would go to use this.
I mean, what is it called? I forget the name. The library for doing neural networks. Are you using
the ARM or something?
Yeah. No. Okay, so we will talk then.
So we have not really touched that one.
You could do it, but that again only uses this very limited kind of DSP functionality. So you want to go. I mean, in my ideal world, you use the Mac for most of the DNN stuff, and if somehow some specific functionality doesn't work for that, then you might go to the ARM library and use the DSPs there.
I see.
So if possible, you would use the accelerators that we provide there.
Right. I see. And those libraries which are, you need both low-level DNN libraries. Those accelerators are the item to it. Yes?
Okay.
The accelerator, I mean, to program the accelerator, I need item number 2.
Yeah, exactly.
Yes. But and the communications, which is number 3.
The communications, you would use low-level SpiNNaker packages that are currently integrated. You know, the single chip, they are kind of working, I would say. It's still a bit handcrafted, but you have support at least on the single chip base for 150 cores using the low-level mapping software from SpiNNaker 1. Yeah.
Okay.
So when you have SNN that is small enough to run on one chip, or let's say that it's not big enough to need multiple chips, then you can use this first one, this SpiNNaker 2 package. And you won't have to touch the other one unless you have really some very specific neural models.
Yeah. And currently, maybe one thing about the size, the easiest at the moment is to just use the SRAM, of course, on the chip. That's out of all those packages. The DRAM interface is in principle working, but now getting it up to speed for transformer implementations. So that's a bit of work in progress. So in principle, yes, we can do stuff with the DRAM already and go to bigger models. I mean, you've got 2 gigabytes of DRAM with each chip, but let's say you can start it in this workshop, but it won't get done in this workshop because it's still maybe a month or so out before that becomes stable.
Okay.
Right. So this is a slide about software installation. I will not really go into that here because we have created some documentation for people who want to use SpiNNaker, and we have a Slack channel, so we can go into the details later. So let's talk more about the SNN software API. This is using the SpiNNaker 2 package, and the way you define networks is really similar to Pine. So you just create populations, and in each population you define the size of the populations, how many neurons, the neuron model, and the respective parameters of that model, and just give it the name. Now the supported neuron models so far are just decay-integrated wire neurons with or without delay, and also with exponentially decaying synaptic currents. You can also have like a spike list as input, so you can define spike times when your input spikes come in for your input neurons. So this can also be used. And then, yeah, you define the parameters of the neurons as dicts, and then you can just pass the measure here. Right. And then to define connections, you just create projections. So projections take a pre-population, a post-population, and then a list of connections. So connections are indices of the neuron index in the pre-population, neuron index of the post-population, the weight, and the delay, if you're using delay. Now, the weights are integers in the range of -15 to 15 if you're using the leak integrate empire with delays, because then 3 bits are reserved for delays. If you do not use delays, then you can just use the 8 bits for the weights. Yeah. And this is also configurable. So if you want to use delays, you can configure the number of bits used for delays to make it smaller. So yeah, and then after you define a network, so all the populations and connections, you just instantiate an object of this network class and add your populations and projections. And then you just map it to the hardware. So you have to create a hardware instance as well. If you're connecting the board with the Ethernet, you have to provide the IP address of the board. And then you add your network to the hardware and you just run it for the time steps that you define.
And the equations for your neurons is in what paper?
The equations are in this S2 Simulab. Yeah, this is the C-level, low-level code.
I see. So right, so someone has to get the code to get what equation. I see. You guys have a different paper or something?
You have a paper on SpiNNaker too, but it does not go into the details of neuron models.
If I wanted to write a C implementation of another neuron model, would I just go there, simply differ, basically?
Exactly. This is easily modifiable.
Yeah.
So there's also a wiki where there's basically a description of what you have to do to create a new neuron model.
Well, I see. What is that?
And it's in this. So this SpiNNaker 2, it's a GitLab project, and in there is a wiki. I think
it's going to be mentioned.
Yeah, it's going to be
mentioned.
Here. That's like.
Okay.
Yeah.
Just to check, are those slides going to be uploaded onto Slack?
Yes, please. So we'll upload it then to the SpiNNaker 2 Slack channel.
Thank you.
Right. So yeah, after you run your network, you can also define recordings. The spikes get recorded automatically, but you can also record voltages. And then after running the network, you can get all this data back. You can plot it or do whatever you want with it. So yeah, let's talk about the current limitations of the SpiNNaker 2 chip. So right now we have limited simulation times. So you can only simulate the network for a few hundred time steps. And this is because the DRAM is still not in use, but this is expected to come soon. There's a limited number of neuron models. So as I said, we have a leak integrate empire neuron. There's a implementation of Izakevich neuron on a dev branch. But yeah, it's not that difficult to add neuron models, right? Because you have examples, you can start from, you can just modify the equations to fit your needs.
So do you have pipelines? Sorry.
No, you have to. We take. Wait. Okay.
Stable loop. It's because of the delay.
Okay, so do you have pipelines for doing the neurons, or do you just use standard ARM? You have specialized pipelines for doing the neurons.
What do you mean?
Many pipelines.
No, not a pipeline. You've got numeric accelerators that help you with part of the neuron equation. So if you look up how a neuron is coded there, you basically see the access calls to the library that calls the accelerators for whatever X block and this kind of stuff.
I see.
It's not like in Loihi where you're actually piecing together basically a neuron in an instruction pipeline. The neuron code, what's regular software runs in your ARM core, and for specific parts, basically calls over like synaptic operations again, like exponential indicates.
For those there is a wiki for that, so someone can build an easy image neuron if they want to set something.
It's already there in the dev branch. So you can check it out.
Okay.
Jason.
So with this limited simulation, as that implies things being stored in memory across time, is there a way to turn? I assume that's probably for something plastic, with synaptic plasticity. No. What's being stored over time?
I think just memory potential. Yeah.
It's quite often you don't need. I mean, don't always need that. Right? If you're doing something online.
So you mean online plasticity?
No, not even online plasticity, just running something online, just pure inference online.
Yeah, so currently what we've actually done that for the radar, right? That ran longer and didn't record.
Yeah, we're trying to
For the radar example.
yes.
So but it's doable. We've had in the BMW, we had the SpiNNaker running, basically doing radar processing. And it was definitely for longer instance time.
But per default, this is now only a batch simulation. So basically you define, okay, this is the input data, you send the input data, it will run the given number of time steps and give you back the results basically. Right.
And there is a multi-run example on a dev branch as well, where you can just change the input and run the network again. So this, for anybody who's going to use SpiNNaker for the control stuff, this is what we will need essentially.
And that's right, we can do real time.
There's real time input as well, but this needs some manual steps because you need to send the data to specific memory addresses and so on.
So how does the code handle the events that come in spikes? Is it a buffer and defaulted in the C code, or is it like some interrupt that is triggered, or like so?
Incoming spikes coming from where? From the
neurons,
coming into the core.
Yeah,
you basically accumulate them for, you can configure that default it's a millisecond. You accumulate it for a millisecond, and then basically the core has a prediction model because it's also QiNS, right? It adjusts its voltage and frequency. So it's looking at the spikes, it's looking how much activity comes in, it does a simple prediction how much clock cycles it needs to compute that away, and then next millisecond it starts processing that stuff.
Okay. And so from the software, from the perspective of writing code for that, you would write a function that gets called with a buffer of spikes that have arrived in the time window, or is it? I'm just wondering like how you would write a code, for example, that would treat like if some spike comes in, do this specific thing. How you would write that?
So you would write, I think you just have to pause the simulation, check your spikes, and do whatever processing you want to do.
But it's actually usually done in the background. You don't do that.
No, but if you want to, I think he wants to do some special processing on the spikes.
Okay, but if you just define a synapse and say whatever spike from neuron XYZ needs to go into that synapse, needs to get that processing, and that's actually handled by the background software. Okay.
Yeah, so incoming spikes trigger memory.
Yeah, okay.
Just a quick follow-up on the online input example. So we've been working on the SpiNNaker 1 to feed quite large distribution DUS schemas directly into the input layer. So that will require quite a lot of neurons, right? And will probably be quite difficult to sit if you want to map to individual address spaces. Is that something you're considering to also support the way SpiNNaker 1 does it, or is there different?
So I'm not really familiar with how SpiNNaker 1 does it.
We would have to look at the, I mean, again, for this particular example, we debugged in the last 1 or 2 months this radar processing that was actually quite high data rate. So we just need to look at how they did it in that code, Bernard and the others.
So I'm not particularly sold on that specific method, but having a way to then map it to neurons would be very useful.
Yeah. So again, the code is there, we've done it, so we just need to figure out if you want to do that, how to port it over.
That would be excellent.
So maybe we can go a little bit into the details of what is happening behind the scenes once you define a network with this high-level Python API. So your network description gets then passed to this mapper module, which then it maps basically the neurons and the connections you define to the actual cores on SpiNNaker. Right? And it creates this hardware specification that then gets mapped to this experiment runner, which is just a C++ code that is executing the stuff on the chip. And it simultaneously creates this, this map model between your virtual neurons in your code and your actual neurons on the cores. And this is in order to, after the simulation has been run, you get then all the data back, and then this is mapped. This is then translated by the mapper back to a way that Python can read these recordings. Right? how long we have to execution of one sample?
Yeah, something like a few seconds. So the few seconds, the most of the time of that is actually transferring the probe, the software into the SpiNNaker, because basically every time you run this, you will transfer the software in, and also all the input data, and you receive back the output data. So the running itself is, you don't really feel it actually for those problems that we've tried with a few hundred neurons.
So there's a config step at the beginning, and then afterwards it's really nice.
Just quickly, I mean, maybe from my understanding, right? So let's say you want to have this online situation, right? You basically want to avoid the mapping when you feed in the data.
So yeah, exactly. You do it only once, and then you feed in real time your input data to specific addresses. This is why it's a bit more complex to set up.
That makes sense.
But it's doable. Yeah. Yeah, okay. Here's some more details of like what is happening in the background. So this hardware experiment specifications, it gets basically a list of the active PEs processing elements cores on SpiNNaker. So you get like an X and Y index, and then the index between in the quad core, and then the memory files that needs to be loaded, and the duration of the simulation, etc. So these are like low levels details that I don't think you really need if you're going to use this Python API. Yeah, and here's I think the recap, right? So this mapper parses populations and places them to available cores, right? There's some details here. So one core or one PE can only support one neuron type at a time, so you cannot have multiple neuron types of one core. If you define large populations, we're talking about that. So each core has a capacity of the number of neurons and supported, depending on the neuron model. So if you're talking about leaky integrated fire neurons, it's 250 neurons per core. If you define a population that is larger than that, then this mapper will automatically map this population to multiple cores.
So to maybe also give a thing here, because we're talking about way less neurons than what we discussed, good, for example. The thing is that at the moment, the neurons in the synapse pretty much run exclusively in the ARM core with the EXP and log accelerators tied in for neuron stuff. What we have not done, integrated this software stack because it's work in progress, is this GNN type mapping of the synaptic input to the MAC accelerator. So that will easily increase the capacity by factor 10 because it's all defined by the synapses, not by the neurons. So right now we're limited by doing a lot of stuff still in the core, which could actually be mapped to the MAC array. Because the MAC array we're pretty much at the moment using for the machine learning test case, but not for the spiking one so far.
The mapper also parses the projections and connections and creates these routing tables that basically say, okay, incoming spikes where they have to be delivered to which core, to which neurons, right? As I said, the experiment specification, like the memory files, recording regions, if you want to record voltages, you have to specify the extra simulation duration. And then the SNN is executed using this experiment runner, so the S2 chip, the C++ code, and then the results are then routed back into the Python API. So now we can show a small demo of a hybrid network that is running on SpiNNaker. So it's really simple. It's just an MNIST classification, and it's a hybrid network. So you have a conv to the ANN layer. So you read the image, get the outputs of the conv layer that is then being fed as currents in an integrated fire neurons. They generate spikes, move them over to another layer of dense integrated fire neurons, and then generate spikes, move them to output layer that is just an integrated, so no spikes, just voltages. And then taking an argmax over the voltages in the output layer, you get the label classified. And this is, if you define this network with the SpiNNaker 2 library, then this also gets automatically mapped to SpiNNaker. So in this case, this network is running on 3 cores in SpiNNaker 2. Here's just some results of that. So here you see the output voltages of the neurons simulated over 50 time steps. And yeah, the winning label here is number 6. And the accuracy is also identical with that TensorFlow model. So in this case, it's not training on SpiNNaker, right? It's just inference. So there's a TensorFlow model that you just load the weights of and yeah, quantize and for this one.
So actually, this is trained directly in TensorFlow, non-spiking, and then the weights are just transferred and quantized.
And this example is available in the repository that you can look at. Right. So yeah, let's come to how to use SpiNNaker 2 during this workshop. So we have set up a demo laptop here. You see on the right, set up with 3 SpiNNaker 2 boards connected to it. We created a SpiNNaker 2 channel on Slack that you can join if you want to use SpiNNaker, and we pinned also like a document with the necessary steps you need to take to use SpiNNaker. So we have to give you an account on this laptop that you can SSH into. We have to give you. You need to send us your GitLab handles because we need to give you access to the Sim2 S2 Lab repository so you can install the low-level stuff. Yeah, and then you can take a look at the examples and start working. And then yeah, we also invite our partner. We can invite them and others to join the Slack for additional support if you have questions.
Yeah, exactly, because the guys who know exactly the real-time interaction are still in Dresden, but yeah, they offer to share here. Maybe in terms of resources, there is quite a number of benchmarks we did last year in Telluride. There is stuff we did in the interim time, like an EPROB implementation. So I think that's all there in GitHub, right? Mm-hmm. So really, apart from these small kind of tutorial-like examples, if you do something bigger, you don't have to reinvent the wheel. There is actually, I think, I don't know, 20, 25 different things that we've done on SpiNNaker so far, so you can really look those up.
Yeah, that's it.
So if you like, I can also just show it how I run this hybrid SNN model, if it works.
Before you mentioned you did leapfrog on SpiNNaker.
Yeah.
So that's a way to extract gradients somehow.
How was it? Implementation. It's actually a Frontiers paper, so we would have to look at it jointly.
I think you can implement it in the low level. So there's also last Telluride, they also did some work, Hector and Timo, I think, on implementing event prop concept.
Okay. Something about extracting gradients from some trace.
Gotcha. So it's definitely doable. So
and of course, if you want, for example, to do floating point based learning, I mean, you can't do it dense because we've only got this, we don't have a MAC array. MAC array is fixed point. But like in EPROB, we actually using, and for some other stuff like the synaptic sampling, we are using the floating point unit, but it's only a single one per ARM core. So this type of stuff needs to be sparse.
Yeah. Here, you know. So basically, you just SSH into the laptop. Yeah. Okay. And then I just go into the directory, some examples. So there's this hybrid example. And yeah, I just have still to activate a Python virtual environment. And in here, we already have a trained TensorFlow model. So if you like, you can also have a look at the Jupyter notebook of that. That's also here. But basically, just Python and then the SMN.py. And yeah, maybe I have to zoom out a little bit. I think it's still readable here. So basically, there's a lot of output here. TensorFlow is loading. The MNIST dataset is being loaded. And yeah, so basically here it starts. So we've selected just one of the examples from the MNIST, which has the expected label of 3. And then here is just some output from the mapping. So for this pretty much toy example, it decides that it needs 3 cores out of the 152. Yes. And yeah, the simulation should be this length. 0.0.
What is the model architecture?
So what's the hybrid one and then two them stay the same?
That was the one just up on the slides.
Yeah, that's good.
So basically, yeah. So there's a conv2d layer at first. Yeah, so I don't show the full code now, but basically we've loaded the code before and just have to scale it for doing the quantization to an 8-bit integer. We instantiate the neurons with some parameters. Then the first hidden layer, again, instantiate the neurons and the projections also. Instantiate the output layer. And then here we just define the network, give all the populations and projections, and yeah, instantiate the hardware and run it. And basically then already we get back the results. Yeah, and here is basically, that's where the software starts. So it just does some low-level configuration. You can ignore that for now. It loads some kind of software into each of the processor cores. And yeah, and then it starts an interrupt to let all the cores start synchronously. And it runs the experiment. And at some point it finishes with some exit code. This code just means that everything went okay. And yeah, then it reads back from
how much words can you cram in X, right?
Yeah.
There's beef, coffee, baked, all the usual stuff.
Yeah. Basically, then it just reads from different memory locations. So it will also just output. So each PE can also have some kind of logging. So basically, that's a printf. It will just go into a certain memory area. That's a lot of what you see here. Yeah, and there's just some output. It then shows, yeah, that's a population of neurons and information to them. Yeah, it's a lot of information here. It doesn't make sense to go through all of it. And at the end, it just reads back the recorded spikes from each of the layers. Yeah, and what's not done here, but what you could do is to also plot them, of course. And actually, the predicted label was labeled 3, and that was correct.
How would we do the user mapping? I mean, use one of the 3 boards over there, and they've got key addresses, right?
Yeah, so that's all in the documentation on Slack.
Yes, so we have 3 SpiNNaker boards. We should try to somehow distribute people on the boards. So at one time, only one person can access one board. So this is handled by having some log file. So in some temporary directory, there's a log file. And as long as one person has the SpiNNaker board actually in use, so as long as the Titan software here is running, the board will be logged. If the software crashes, the log might still stay there. And then you should, you have to delete it manually. But by default, it's deleted after the software finishes. Okay, so yeah, if you want to use the board, just talk to us and we can figure out who uses which. Yes, please.
So there's a more open-ended question I'm happy to pick up afterwards as well. But I've seen you do a lot of great stuff outside spiking networks as well, also with some kind of ML modeling, deep learning graph system. I'm wondering how you envision the integration in this context, right? Because of course, Parn is one way to take your graph of sorts and map that onto the cores, right? Do you see any kind of collaboration or integration with the machine learning part of things?
My preferred model is what we've been, I don't know if you really got the question, but my preferred model is what we've been pushing out on the last couple of NeurIPs and ICML and ICLR, which is basically we are gating at various levels RNNs and DNNs. One version is, we call it EGRUs, event-based GRU units, where we really try to think of networks as neurons and basically threshold those. So that's kind of taking it one step further, going for dynamic sparsity at whichever level, not necessarily doing SNNs, but doing kind of SNN coding of DNNs and RNNs. So that's one version of hybrid. The other version of hybrid could be something like here. We actually did something similar for the radar processing chain. Right. So that's also kind of CNNs feeding into LLF neurons, feeding back into max pool layers. So you can also do this layer-wise in a sense.
Yeah, so an abstract of this makes wonderful sense, right? Because you can kind of abstract both concepts into the same component, basically. My question is a bit more practical, right? Can I do that right now? Can I take the idea?
This is basically it.
But how general is it, right? Can I do like values and all the conventional machine learning stuff?
Like as long as your activation is 0, then it knows how to handle it. That was fair.
I mean, what you can define at the moment is CNN and fully connected layers. So the usual stuff. We've got a softmax function implemented, I think. We could use that. We don't yet have attention heads in this more complex machinery as a finished block. So you would really need to plug those together from bits and pieces. But the individual functionality, like Guido's, it's all there, yeah.
And this okay, yeah, I'll talk to you about it afterwards. Thank you.
So like dynamic sparsity.
Come again?
So you like dynamic sparsity. What about sparse weights?
Those as well, but of course, there's one caveat. We had kind of design freeze of SpiNNaker like 2 years ago, and our ideas, especially Matthias also did on this, couple of accelerators, where we really do kind of very weight individual and neuron individual sparsity support. It's not yet there on SpiNNaker. SpiNNaker works best really if you can do kind of block level structural and activity sparsity. That's why we're looking at these kind of population level gatings, where they can do basically use the entire MAC or you don't use it. But we don't have stages like you have in edge nodes, or like we're also doing our edge nodes, where you have multiplexers in front of the MAC, where you basically even can compress individual neuron and synaptic matrices that you're using the MAC in an efficient way.
So if you're getting individual neurons in order to block out a bunch of weights being used, that still kind of feels like dynamic sparsity in a way, so that spinning out of 0.
To a certain level, it also gets you something in SpiNNaker, because then we just compute this faster basically on the MAC, right? But it's not the full level kind of very individual weight dynamic sparsity support. Yeah.
Okay, that makes sense.
There was a question on the chat there, another one. One question in the chat about will it be possible for online people to somehow get remote access to that?
Actually, there's a board in Dresden who's remotely accessible the entire time. I don't know if we really want to do it with a touchy network. We want to do it with both boards, but you can definitely access the board. I think multiple boards that are available in Dresden.
Yeah, that would have to contact them. That would be awesome. And then I missed what the second question was that popped up briefly.
So yeah, if you're interested in that, please just contact us directly, and we can try to make it work.
Yeah, and then
this follow-up question the one of Jason. If you have like sparse activations, the sparse weights are not yet supported.
Sparse weights, as long as it's kind of block level sparsity, then it is supported. Yeah.
And what about the individual neuron? If you have binary activations, are given taking care of the sparsity? I mean,
what do you mean?
If you have a sparse activation, but it's not sparse,
yeah,
but it's not very structured, then would the SpiNNaker take care of the sparsity computation?
In essence, you could always run that just through the ARM core, and you don't use the MAC. And of course, on the ARM core, you could support individual sparsity, right? You just close down the ARM core after you've computed this stuff away.
But the question is whether it's event-driven.
So in this SNN framework, it is definitely. So it will only send out a packet or some data to another PE when there's actually a spike.
Yeah.
And it will also only send out the spikes.
Yeah, that's true. And the DNN framework at the moment is still kind of frame-based. Yeah.
So when we do DNN, it's really at the moment fully dense, basically.
Okay. So we won't win if anything extra if we made our DNNs sparse. Is that fair to say?
Except if there are many zeros.
At the block level.
Yeah. At the block level, or as I said, in some cases, we figured out it really makes sense to support this individual spike. Don't go to the MAC at all.
Yeah.
Do it with the floating point units or whatever on the core, and that way you can, of course, support very individual kind of sparsity.
Yeah.